Dear colleagues, it is my great pleasure to welcome everybody to our first day, day one, of our Artificial Intelligence in Ophthalmology meeting 2023. This meeting is organized by International AI in Ophthalmology Society, our foundation Ophthalmology 21, University of Varmia and Missouri, and Academia Europea. Here we see our team of Foundation 21. All of members of our team were involved in the preparations of this meeting. And just a few words to introduce one of our co-organizers, Academia Europea, the Academy of Europe, was established in 1988 and is the Pan-European Academy of Sciences, Humanities and Letters. It's a non-governmental association acting as an academy. Our members are scientists and scholars who collectively aim to promote learning, education, and research. As I mentioned, it was founded in 1988 with more than 5,000 members, which includes leading experts from the physical sciences and technology, biological sciences and medicine, mathematics, letters and humanities, social and cognitive sciences, economics, and the law. I'm very proud to be one of the members of this organization. Our sponsor, industry support comes from Zeiss company, and our media patrons are the International Ophthalmology magazine, Ophthalmologists, and the Polish medical platform Medycyna Praktyczna. Just a few words about our society. It's an International AI in Ophthalmology Society. It's a non-profit society to integrate both healthcare professionals and computer scientists to share important initiatives, scientific knowledge, and practical applications of AI in ophthalmology. The society should be also involved in supporting legal regulations protecting the responsible introduction of AI to healthcare. So we invite everybody. The registration is free. Everybody can easily register on our website, become a member, and then become involved in our initiatives. So please remember about our website. Today, we have 4 sessions. We start with the basics in AI in ophthalmology, and then we will, this is the most educational session. Then we have the innovations, new applications of AI in ophthalmology in the session number 2. Then session number 3, practical implementations of AI in ophthalmology. And session number 4, what do ophthalmologists expect from AI? We will have a very interesting introductory lecture by Professor Schmetterer from Austria and Singapore on limitations of AI applications to ophthalmology and how to overcome them. And then we'll have a panel discussion with invited speakers as the list here is shown. So welcome again, everybody, to our today's meeting. I would like to remind you that tomorrow we have the Day 2 conference. The program can be easily found at our website. However, please remember to register separately to the Day 2. In order to have access to the meeting tomorrow, you need to do the registration separately. Moreover, please send us the questions to our speakers as soon as possible on the chat. So when you have the question, please put it on the chat, because we do sometimes experience some delay in receiving these questions, so that then might be a problem to share this question. Unfortunately, some of the speakers will not be available during the discussion, Well, we know we live now in a global world, and it is sometimes related to the time difference. Sometimes they are busy with other, let's say, obligations. So, but all of them provided the email addresses, and we will show these email addresses at the beginning of the session, at the end of the session, and also we added all the email addresses to the program, and they declared that they will respond to any question because some of them, I mean, about those who are not present during the discussion, they will respond to the questions by email. So please also use this opportunity. Now we can move to start the first session. May I have the slide of the first session, please? Poproszę o slajd pierwszej sesji, ale go nie widzę. Started and opened the first session, Basics in AI and Ophthalmology, and introduced our speakers. The first speaker is Professor Michael Goldbaum from University of California in San Diego in United States. And Professor Goldbaum began teaching ophthalmology at this university in 1977 and is respected worldwide as a visiting professor at university in China, Paraguay, Italy, Ukraine, and as a Stanford University and Columbia in the US. His research interests include the surgical and medical treatment of retina and vitreous, macular degeneration, pediatric retina, ocular tumors, and glaucoma informatics. The second speaker is Professor Pearse Keane, who will speak on AI in retinal disorders from Moorfields Eye Hospital and University College London Institute of Ophthalmology. And his research interests include retinal imaging, optical coherence tomography, AMD, retinal diagnostic and therapeutic challenges. The third speaker, Dr. Wiktor Stopyra, from Krakow, from Poland, will speak on AI-based IOL calculation formulas. And then Dr. Louis Arnould from Dijon, from Ophthalmology Department of the University of Dijon, will speak on AI of the eye images to detect non-eye disorders. Dr. Arnould is an ophthalmologist specializing in refractive surgery, corneal surgery, cataract, and glaucoma surgery. He was trained at the University of Burgundy, where he completed his thesis. He's the member of the European Board of Ophthalmology and the International Glaucoma Panel. And Professor Xiulan Zhang from China, from Guangzhou, she will speak on AI in glaucoma, present and future. Professor Xiulan Zhang is a glaucoma specialist and, of course, professor of ophthalmology at the Zhongshan Ophthalmic Center, Sun Yat-sen University in Guangzhou in China. She has been dedicated to clinical practice, teaching, and research in ophthalmology for over 30 years. She was nominated for top 50 expertise in glaucoma worldwide in Expertscape from 2020 to 2022. And she was also included to the top 100 ranking of most influential in ophthalmology by Ophthalmology Power List in 2023. So let's start the recordings now.
This primer about AI is designed to familiarize you with the concepts of artificial intelligence in preparation for the presentations that follow. I have no financial interests or relationships to disclose. AI is a wide field comprising robots and machines making decisions. Deep learning networks are a subset of machine classifiers that are capable of learning how to make sophisticated decisions. At this point, I would like to give a bit of history of the beginning of AI in ophthalmology. The first application of AI in ophthalmology was to diagnose images of the ocular fundus. The initial approach used lesions and anatomical structures in the image. The first extraction of blood vessels and the optic nerve was in 1989. The first application of neural networks to diagnose images of the ocular fundus was also in 1989. The first diagnosis of glaucoma from automated visual fields was in 1990. And the first approval by the FDA for a device to make medical diagnosis was for the IDX in 2016 to diagnose diabetic retinopathy. In 1822, Charles Babbage designed the first computer. He declared that machines can do only what we tell them to do. We have recently discovered that without our intervention, machines can do a lot more than that. Initially, we wrote code that gave detailed instructions for the computer to do anything. This is arduous, and new code must be written for each new task. With artificial neural networks, computers learn from the data what needs to be done. Emulating the neural networks in the brain, computer neural networks can learn from vast amounts of data, millions of times larger than what we learn from. The computer neural network is made by assembling computer neurons that are modeled after biologic neurons. The biologic neuron takes input from multiple dendrites, processes the input, and gives an on-off output in a single axon with branches. Similarly, a computer neuron accepts multiple inputs, processes weighted inputs with a step function, and gives a single binary output of 0 or 1. These neurons are assembled into a network that learns from a dataset of examples how to make an accurate decision. The weights of the connections make up the knowledge in the network. There are many architectures for neural networks. Shown here is the multi-layer perceptron, a commonly used architecture in current systems. A multi-layer perceptron with a single layer, seen on the left, can effectively learn to make simple decisions. A deep neural network with hundreds of hidden layers has the capacity to learn complex analyses from vast numbers of examples. Why is it that neural networks perform so well? Statistical classifiers in common use before neural networks separate the data with a line, plane, or hyperplane. This leads to many false negatives and false positives. Neural networks create separating surfaces that adapt to the data, and these adapted separating surfaces greatly reduce the number of false negatives and positives. The next principle concerns the way that networks learn. Of the many methods of learning, two are most important for us. We will use the diagnosis of glaucoma from visual field tests as an example. With supervised learning, the visual field for each example is accompanied by a label with the correct diagnosis. The diagnosis label helps the classifier to learn to distinguish between normal and glaucoma. In unsupervised learning, the goal is not diagnosis, but disclosing the patterns in the data. On the right, you can see that without any human intervention, the network has discovered in minutes the patterns of visual fields that match those discovered by human experts over years. How does the network learn? The knowledge is in the weights of the links between the neurons. The weights in the links initially are random. The proposed output is compared to the correct output, and the errors are propagated backward to adjust the weights to reinforce the correct responses and diminish the incorrect responses. This is repeated hundreds of times until the network completes its learning. If we let this graph represent the error surface, the highest error is at the beginning, and eventually we reach the minimum error. A properly tuned learning does a ski run down the error surface. With each epoch, the error is reduced by gradient descent, trying to achieve the absolute minimum. This slide shows how a generic ROC curve is generated. We would like to demonstrate the performance of a network with a single number. These two curves are the distribution of the classes, for example, normal and glaucoma, for all the samples in the test. The sensitivity is the percentage of glaucoma properly identified as glaucoma, and the specificity is the percentage of normal properly identified as normal. As the threshold for declaring the proper class moves from one extreme to the other, the sensitivity and specificity pairs are plotted. The area under the curve is a single number that represents how well the classifier is performing. 0.5 is equal to chance alone, and 1 is perfect performance. Another principle is that the test set must be different than the training set. Using the training set as a test set leads to overperformance of the network. Holdout, cross-validation, and bootstrapping are common methods of separating the test set and the training set. The original method for diagnosing fundus images is a step-by-step paradigm that interprets fundus images in 3 steps. Step 1, lesions and anatomical structures are segmented. Step 2, the segmented objects are individually classified and labeled. And step 3, the image is diagnosed based on the contents of the image. This step-by-step approach can be successful, but it is arduous to develop and is specific to one problem. Deep neural networks are the advance that has made AI so revolutionary today. With hundreds of layers and millions of connections in which to store the knowledge, deep networks can analyze problems greater in complexity than human minds can. End-to-end analysis takes the image as input, subsumes the 3 steps previously described, and directly gives diagnosis as output. For example, an input of 480,000 pixels in an image of the optic nerve head can lead to the diagnosis of glaucoma from normal and even predict glaucoma onset in the future. As a more recent example, chatbots, learning from sentences in practically the world of literature and knowledge, can express remarkably sophisticated information in cogent text. Physicians don't trust diagnoses without knowing how they are made. Neural networks started out as black boxes. Class activation maps and occlusion are popular methods to peer into the black box to explain how the decision was made. With occlusion, each portion of the image is removed, and the location that most affects the performance can be found. With the class activation map, the last layer where the most sophisticated information is found is analyzed to locate the part of the image that is most important. It should come as no surprise that the inferior temporal and superior temporal nerve fiber layer is most important for separating glaucoma from normal. When we learn to read images, we start with a visual system trained since birth on a world of images. Pre-learning from a wide variety of images makes it easier for the network to learn the task of diagnosing medical images. After pre-learning, the weights are frozen. The last layers are not frozen, and they are permitted to learn the task of diagnosing OCTs in this example. AI can find abnormalities that we can't. Whereas we can't predict which of these eyes will develop glaucoma from the appearance of the optic nerve, this neural network could predict glaucoma up to 7 years in advance. Now that we have the basic concepts under our belts, let's see some applications. One application of the transformer model is natural language understanding. The transformer uses the sequence and importance of words to develop the relationships of words. These relationships then provide semantic understanding and domain expertise that form knowledge. In generative networks, the knowledge base is used to generate and refine output. In this example, we have a number of synthesized images of the ocular fundus. Before we see their applications, let's review the AI principles. Deep learning uses a massive complex of computer neurons to analyze massive data sets. Unsupervised learning finds patterns in the data and does not require the arduous labeling of data. Pre-training develops knowledge, and generative networks synthesize outputs from the knowledge. In a similar fashion, we can see the same principles used to construct ChatGPT. The transformer model parses a query from the user. The transformer model also parses text to find parameters for the teaching set. ChatGPT's training set contains 45 terabytes of text and 1 trillion parameters. Sources include web text, books, Wikipedia, and Common Crawl. Pre-training with unsupervised learning finds patterns to build knowledge, and generative output gives feedback in well-formed sentences. Other benefits in medical care include extending our capabilities with telemedicine to help diagnose or manage patients in remote locations, providing decision support and advice, for example, guiding us to obtain the next best information in the workup of a puzzling patient, working ceaselessly on drudgery, freeing us to do what we consider more important, and expanding our knowledge and improving our empathy. So I hope I have demystified AI and prepared you for the lectures that follow.
Hello, my name is Pearse Keane, and today I'm going to be talking about artificial intelligence in retinal disorders. If anyone would like to get in touch with me, I've included my Twitter handle on the bottom right of this title slide, and on the last slide of my presentation, I'll also give my email address. So first, a little bit about my background. I'm a consultant ophthalmologist at Moorfields Eye Hospital in London, and at Moorfields I specialise in the treatment of retinal disease. And I'm also a professor of artificial medical intelligence at University College London at the Institute of Ophthalmology. And although I'm not a computer scientist and I'm not an engineer, I've somehow come to find myself leading a multidisciplinary research group that aims to focus on the development and application of artificial intelligence in healthcare, using ophthalmology as an exemplar for other medical specialties. I'm very fortunate to be funded by UK Research and Innovation, and here is a list of my financial disclosures. So, why has everybody been so excited about artificial intelligence for the last 5 to 10 years? Well, in December 2016, the New York Times wrote an article which they entitled The Great AI Awakening. And this article described how advances in a subtype of AI called machine learning, and in particular a subtype of machine learning called deep learning, had revolutionized the tech industry, and described how all the major tech companies had pivoted to become AI-first companies. And nowadays, whether it's our smartphones or our laptops or other digital devices, AI is firmly embedded throughout our lives. Now, when we talk about these latest advances in AI, we're typically referring to deep learning. And deep learning is really just another way to describe something called artificial neural networks. And artificial neural networks are computational models that superficially resemble the brain in the way that they process information. And they're typically represented in a diagram like this, where you see layers, multiple vertical layers, each of them having many connections between, and each of these circles here are called neurons or nodes. Now, this is a very simple representation of an artificial neural network, but it really doesn't convey the complexity of these models. And so I thought I'd show you this model this video that I downloaded from YouTube, which begins to put across some of the complexity. So on the left, you can see you put in a two-dimensional array of numbers, and essentially you have a number of different layers then, and the output of the neural network is some sort of classification task. So in this case, it identifies what number has been presented to it. Now, it's important to emphasize that this neural network that I'm showing in this video is relatively simple with only 3 layers and only 2% of the connections are shown. So it's in fact much more complex in reality. And further to that, the state-of-the-art neural networks at the moment, particularly in large language models, often have 500 billion or even approaching 1 trillion such connections. And each of those connections is essentially a mathematical calculation that has to occur. Now, it's been very exciting that ophthalmology has been one of the medical specialties at the forefront of AI in healthcare. And of course, I'm biased in making that statement because I'm an ophthalmologist, but there is some objective evidence to support it. In particular, the first ever autonomous AI system to receive FDA clearance was in ophthalmology, and that was for diabetic retinopathy screening. And this is from the company IDX, now known as Digital Diagnostics. And in fact, the second ever AI system to receive clearance as an entirely autonomous system was also for diabetic retinopathy. And this was in August 2020 from the company iNuke. Now, we also have major companies such as Google involved in AI and ophthalmology. And Google have created a system for diabetic retinopathy screening called ARDA. And they've published a lot of their work associated with this, and their ARDA algorithm has now been used in over 100,000 patients in India and the Philippines and a number of other countries. In fact, Google are closely linked with a company called Verily, and Verily have created this portable, low-cost retinal imaging device, which can be combined with this artificial intelligence, and they believe that this could have major impact, particularly in low and middle-income countries. Now, there's a number of other diabetic retinopathy systems which are available, and so Google have partnered with Nikon and with Optos. And so in the European Union, we have the Optos AI solutions now have received CE marking and are available in current commercially available systems. So you can take a wide field fundus image with your Optos device, and you can upload it to the cloud, and then within a minute or two, you can get automated measurements of whether there's diabetic macular edema, whether there's proliferative diabetic retinopathy, and a number of other useful reports. Now, my own work in this space really began in 2015 and 2016, where I initiated a research collaboration between the hospital where I work, Moorfields Eye Hospital, and the artificial intelligence company DeepMind. And DeepMind are a company that were founded in 2012 in London, acquired by Google in 2014, and are arguably one of the world's leading artificial intelligence companies. Now, essentially, we created an algorithm that could be used in cases of suspected macular disease. So in particular, this runs on macular OCT volume scans. So if a patient goes to their optometrist, their optician, or a comprehensive ophthalmologist in the community, and the practitioner thinks that there's some sort of macular disease, they do an OCT scan, and essentially the AI system will analyze the scan. It will first of all delineate all the different anatomic and pathologic features on the scan, and then it will give a classification output. So in this case, you can see on the top left, it makes a referral suggestion to a retina specialist. So in this case of wet AMD, it suggests urgent referral, and it also gives a diagnosis. So in this case, it's diagnosing choroidal neovascularization, 98.5% certainty. Now, there are a number of other companies that have been looking at applying AI to OCT scans, although the focus has typically been more just on measurement of fluid to guide retinal specialists in the delivery of intravitreal therapies. So there's a company called Retinal from Switzerland that have been working in this space, and also developing an image management system to help in the post-hoc analysis of clinical trial data. And then from Austria, we have the company Retinsight, which also has a regulatory cleared in Europe device that does fluid measurement in patients with neovascular AMD. Now, of course, there's multiple challenges to the translation of AI in healthcare, and more specifically in ophthalmology. So we have hundreds or maybe even thousands of papers, but very, very few, if any, have actually translated to the next stage of widespread clinical use. And there's a number of reasons for that. So I think most people will realize that clinical validation is very difficult. It's one thing to do a small retrospective validation study on data from your own institution, but how do you do a similar study on data from institutions all around the world? And how do you pair that with regulatory approval? And what are the costs and the expertise that are required to get something like FDA clearance, for example? And that's typically something that can only be done in a commercial setting. Now, those are some of the obvious challenges, but really some of the broader challenges, the really gnarly challenges, are still relatively unexplored. So one of them will be, if you've got an AI system, how do you integrate it with existing ophthalmic imaging vending systems? How do you integrate it with electronic health records? How do you deliver it? Does the data have to go to the cloud, or can the outcomes of the AI system be delivered entirely locally? What are the business models? Who's going to pay for that? Do you pay a click fee for use? Do you have a subscription fee? Is it something free? Or what makes sense in terms of these things? Because, of course, one of the challenges is if you're going to charge every time it's used, then many healthcare systems, particularly in public settings, will want to have evidence that it leads to better outcomes. And that requires large clinical trials with huge costs associated. And then what about implementation and adoption? So will ophthalmologists, will retina specialists actually want to use these systems? Will they feel threatened by these systems? Will these systems fit seamlessly into their workflows, into the patient pathways? And we know that if there's even a delay of a couple of minutes in a patient pathway, then that might be enough to prevent it from being actually clinically useful. So the comparison that I make actually is with the dawning of the electrical age. So I've read a lot about Thomas Edison in the last few months. And Edison is commonly thought of as being the father of the electrical age. And so this article, published in 2014, says that on September 4th, 1882, the electrical age began. And so that was the day that someone from Thomas Edison's Edison Illuminating Company flipped a switch on a power station in Pearl Street in Lower Manhattan and lit up the whole Pearl Street district of Lower Manhattan. Now, what Edison realized is that it wasn't just about getting a prototype light bulb. In fact, for 20 years before this, there had been more than 20 different prototype incandescent bulbs with similarities to what Edison finally developed. So what Edison realized that it wasn't just about having a light bulb that you could do a demonstration to some journalists. You could get them into a room, watch it light for 2 or 3 minutes, and then usher them out of the room before the light bulb fizzled out. It was about having a long-acting bulb, but it was also about having a reliable source of electricity, having a distribution system, having a connection system, having some sort of meter or measurement system that allowed it to be charged for. And so, in fact, it was a network of innovations that's required. And so a lot of the work that we're doing in AI is still at that prototype stage, where we're showing prototype light bulbs that can actually, only be used for 2 or 3 minutes and only used in very selected conditions. And we don't have all the other network of innovations that are required yet. Widespread use of the cloud, better technical infrastructure, etc. So a lot of what I do is thinking about how the clinic of 2030 will look and how that will be transformed by artificial intelligence. Now, at Moorfields, we're building a new hospital in the King's Cross area of London, and we're hoping that will be finished in 2027. And so we're already working with the architects and the designers of that hospital to make sure that we have the flexibility in the design so we can take advantage of the new pathways that we think AI is going to allow in the coming years. But what really excites me, though, is thinking about what is the potential for artificial intelligence to bring world-class expertise out of specialized centers such as Moorfields and potentially into the community and into the homes of patients in the future. And I think that this can be greatly facilitated by the fact that in many countries, we now see widespread of OCT scans in community optometry settings. And we're potentially also seeing home OCT scanners becoming available in the near future too. So just to finish up then, this has just been a quick summary of artificial intelligence in retinal disorders. I think we're still in the super early stages, but I do believe that this technology has the potential to reinvent the eye examination for the 21st century. And lastly, as promised, that's my email address. I really do like for people to get in touch with questions, or if they want a copy of slides, or they want to explore potential collaborations. That's it from me. Thank you.
Honorable Presidium, dear colleagues, I would like to thank the organizer of this wonderful conference for inviting me to participate actively. AI-based intraocular lens calculation formulas is a topic of my lecture. My financial disclosures. Ernest Hemingway, an American writer, Nobel Prize winner, used to say, "To write an article about Chinese dialectics, you must first read the articles on China, then articles on dialectics, and next combine them." Thinking like Hemingway, let's try to define artificial intelligence first. According to Oxford English Dictionary, artificial intelligence is the theory and development of computer systems able to perform tasks normally requiring human intelligence, such as visual perception, speech recognition, decision-making, and translation between languages. The term artificial intelligence was coined in 1955 by John McCarthy. However, Alan Turing, an English mathematician, is assumed to be a father of artificial intelligence since in 1948 he introduced many of its central concepts. Moreover, Turing used to say, a computer would deserve to be called intelligent if it could deceive a human into believing that it was human. And this is the principal feature of the Turing test. And now a short introduction about intraocular lens formulas. Since in 1967 Sviatosław Fiodorow published the first theoretical IOL power calculation formula, many others have been developed over the years. And traditionally, they are divided by generations. However, the division based on logical approach seems to be much more useful. Formulas using optical approach, data-driven, including artificial intelligence, and hybrids are distinguished. Hill RBF and Carmona are pure artificial intelligence-based intraocular lens formulas. In turn, Full-Monty, LADAS, Pearse DGS, Keane, and Hofer QST incorporate both optical and artificial intelligence components to refine their outcomes. Here is flow chart of intraocular lens formula using optical approach. First, biometry and refractive target is brought in as input data. Then, using optical formula, output is obtained, meaning IOL power. The flow chart is more extensive when artificial intelligence-based formula is used. Let's see. Machine learning formula receives not only input data, but also the training set. Additionally, it has a feedback with the test set. And finally, using such algorithm, intraocular lens power is achieved as output. Different variables are used as input parameters in artificial intelligence intraocular lens power calculation formulas. Axial length and anterior chamber depth are mandatory always. Keratometry is compulsory in all except Carmona. However, anterior keratometry is used in that case. Gerald Clark was a pioneer in the application of artificial intelligence in intraocular lens power calculation formulas. He proposed Full-Monty method, which was a combined system between SRKT and artificial intelligence algorithm called Bayesian additive regression trees, optimized with Markov chain Monte Carlo simulator to produce its refractive predictions. The formula used biometric data such as axial length, keratometry, anterior chamber depth, and lens thickness. Unfortunately, the method is currently not available. In 2015, John Ladas and others, Jeoung, Siddiqui, Devgan, published the concept of intraocular lens superformula with joint advantages of previous models. I mean Hofer Q, Halliday 1 with Koch adjustment, SRKT, and Haggis. First, they found a methodology of depicting these formulas into 3 dimensions: axial length in millimeters, corneal power in dioptries, and intraocular lens power in dioptries. And then they identified best portions of each of mentioned formulas to extend supersurface. The last step was adjustment of existing formulas using deep learning and developing lattice superformula from the supersurface. Dr. Warren Hill from United States launched in 2016 the Hill RBF formula as a pure data-driven intraocular lens calculation approach based on radial basis function network and free of the limitation of lens position estimation. This formula employs pattern recognition developed by MATLAB and a sophisticated form of data interpolation. It has 3 versions. The latest, 3.0, is based on dataset over 30,000 eyes. Input data include axial length, keratometry, anterior chamber depth, white to white, lens thickness, central corneal thickness, and gender. The Pearl DGS formula, named after the formula developers, de Belanier, Retinal, SAT, was published in 2017 as combination of optical biometry and machine learning modeling. The prediction of the theoretical internal lens position as theoretical distance between the posterior corneal surface and the anterior intraocular lens surface, back calculated from postoperative data using various algorithms, e.g. regular multiple or support vector regression, gradient boosted trees, and neural networks, is its main feature. Output linearization and adjustable intraocular lens constants are characteristics for a pure DGS also. The formula uses following variables: axial length, anterior chamber depth, keratometry, white to white, lens thickness, and central corneal thickness. Jack Kay from Australia launched in 2017 his formula, which incorporated both optics and regression and artificial intelligence components. It was based on about 30,000 cases and was developed using cloud-based computing. A focus of the formula was to reduce the errors seen at the extremes of the various ocular dimensions. A constant, axial length, keratometry, anterior chamber depth, and gender are compulsory parameters, while lens thickness and central corneal thickness are optional ones. The Hofer QST formula was developed in 2021 by Kenneth Hofer, Giacomo Savini, and Leonardo Taroni as refining third generation Hofer Q by using artificial intelligence. They aimed to increase accuracy in long eyes. Input data include axial length, keratometry, anterior chamber depth, and gender. The Carmona formula has been designed by David Carmona Gonzalez as a result of pure artificial intelligence without optic components. It is based on 2 combined models of machine learning, meaning regularized Bayesian neural network and cubist decision tree. Formula uses such input parameters: axial length, anterior chamber depth, corneal anterior surface central radius, white to white, and also some optional like lens thickness, anterior segment depth as a sum of anterior chamber depth and lens thickness, corneal posterior surface radius and gender. The main purpose is to improve the exactness in extreme and atypical eyes. Accurate intraocular lens power calculation is a very important aspect of phacoemulsification because patient expectations for perfect vision after cataract surgery are still increasing. The exactness of intraocular lens power calculation formulas, especially for eyes shorter than 22 mm or longer than 25 mm, is still questionable, and there is no agreement among cataract surgeons regarding the choice of the formula. Many original studies have been published on this topic. I would like to present a short review with methodology that follows the PRISMA guidelines. The studies with the maximum sample, I mean over 75 patients, the largest number of compared AI intraocular lens power calculation formulas, over 2, and the most recent ones from the last 6 years were selected. Accuracy of formulas was considered in terms of mean absolute error and percentage of patients within plus minus 0.5 dioptry. And based on Cook's ranking, each formula was assigned an appropriate place in 2 above mentioned classifications. The Kane formula obtained the highest number of the first places ahead of pure DGS. Detailed outcomes of this review will be published soon. Winston Churchill, Prime Minister of the United Kingdom and also Nobel Prize winner in literature, used to say, "A good speech should be like a woman's skirt, long enough to cover the subject and short enough to create interest." I have covered the subject, hoping I have created an interest. Thank you for your attention.
Hello everybody, I'm Louis Arnould from Dijon University Hospital, and I will present AI of the eye images to detect non-eye disorders. And I want to thank Andrzej and Thomas for their kind invitation. We are benefiting from huge advances in retinal imaging, and we are now able to collect a lot of information based on fundus photographs and OCT angiography regarding the vascular network, and we are now able to collect qualitative and quantitative data. On a daily routine clinic, we are using retinal imaging to screen, diagnose and monitor ocular disease, and the idea of this talk is to look for other application of retinal imaging, and if there are any interest to study peripheral vascular system, in our cases retinal vascular network, to study a non-eye disorder. And in our presentation it will be based on systemic macrovascular affection, and I will focus my speech on cardiovascular system. It is also possible to detect neurological non-eye disorder and also cognitive disorder, but I'm not a specialist of this area, and I will focus my talk on cardiovascular risk factors, cardiovascular event, and cardiovascular risk assessment. The name of this research area is oculomics. It is the ability to use ocular biomarkers to detect systemic disease, to predict its future onset, and to provide non-invasive surrogates of its severity and treatment response. It is not possible to replace the old cardiovascular exam, but we can look at these techniques as additional investigation, and the final goal is to reclassify patient compared to current risk stratification scores. Retinal microvasculator and vascular systemic disease study started long time ago. Fundus photographs have been shown to be a very good predictor of cardiovascular major events such as long-term risk of mortality or ischemic stroke. When the vascular network is impaired, the geometric parameters are modified, and a very good sign is the impaired retinal fractal dimension, because it is highly correlated to higher risk of cardiovascular event and major cardiovascular event prevalence. And another way of presenting the vascular network could be suboptimal retinal vascular network, and it has been presented to be associated with treated diabetes and increased heart score. It is also true with the OCTA technique. Less papers have been published in the literature, but it's on the rise, and lower vessel density, enlarged foveal avascular zone have been presented to be also highly correlated to higher cardiovascular risk profile patient and more frequent cardiovascular events. So the point of this presentation is, can we use AI technology, AI strategy to extract information from fundus or OCTA or retinal imaging to detect, screen, monitor or predict non-eye disorder. And one first strategy is to use AI to automatically segmentate the vessel of the vascular retinal vascular network. And one of the first software to be able to build an automatically segmented vessel network is the Quartz software. And the idea is to segmentate either venules and also arterioles, and after that to be able to automatically measure caliber, tortuosity, vessel branching, but also fractal dimension. Another strategy based on retinal vascular biomarkers is the one that are built based on the ground truth traditional semi-automated software. Previous studies have been performed with these software named SIVA, EVAN, Vampire, and the idea is to use it as a ground truth and to build algorithm based on CNN to measure automatically vessel geometric parameters. And Another strategy is to be non-dependent to retinal vascular network parameters and to use deep learning network from retinal fundus. So the idea is the input is pixel intensity of the image and the output is the label data, cardiovascular parameters. One thing that is very interesting with this strategy is that you will get saliency maps or heat maps to highlight image regions, pixels that most contributed to the model's decision, and it's very, very important for patient education and information. And the idea is to evaluate algorithm performance by mean absolute error and IUC. The landmark publication on this topic is the paper published by Ryan Popling and team. They were able to predict with a very high accuracy cardiovascular risk factors, but also cardiovascular major adverse event. And one thing that is quite interesting in this paper is that you have to work hand-to-hand with the algorithm and the score with this, which were the classical cardiovascular risk factors tool. And the idea is you get a higher rate of prediction with both strategy combined, algorithm and scores. So the retinal imaging will not replace cardiovascular risk assessment, but it will refine it, it will fine-tune it. So on this slide you can see the saliency map for the algorithm, and it's nice to see the region that we ophthalmologists are not very used to look at when we are confronted to a fundus. So it's nice to see that without a priori region are also very important for such purpose. Another interesting paper with the Quartz software to predict circulatory mortality and myocardial infarction and stroke. And the final idea of this paper was that the prediction of circulatory mortality was better with the combined strategy, meaning cardiovascular risk factors, usual classical information, plus the retinal vasculometry extracted from the Quartz. So in order to detect, screen and monitor non-eye disorder, we have to think that these strategies are necessarily combined with usual and classical clinical examination. So the literature is very rich on this domain, and I found papers that were predicting carotid artery arteriosclerosis from retinal fundus, the artery calcium score from fundus, and also very interesting work on biological age. So as presented, a very interesting study based on a huge dataset. The good question is, can we do it with a smaller dataset? The answer, of course, is yes. You can work on open data source, and the idea is to go on the multimodal approach. We published a few years ago the prediction of cardiovascular parameters from both fundus and OCT angiography from quantitative data with a machine learning model, and the idea was to estimate cardiovascular risk score, AHA score, syntax and score risk. So as you can see on this slide, the prediction rate were pretty good for cardiovascular risk score, syntax, AHA and score risk, and also pretty good for the cardiovascular risk factors. Our new project to predict and detect non-eye disorder is the EyeHeart project, and we are working on the OCTA imaging plexelite with a CNN architecture algorithm to predict cardiovascular risk profile. So the thing is a multi-label classification of the neurovascular and cardiovascular risk profile of patients. In this research field, we have just submitted for publication the first open data source on this topic. It's a collection of OCTA imaging and very high quality cardiovascular information. So the thing that is very important in this research area is to collect good label variable for the algorithm to predict high quality output from good input. So it will be soon available for international collaboration. Discussion. AI to study large amount of data and cardiovascular outcomes is a very good tool. Algorithm presented very high performances and prediction rates. The good thing is to work without clinician a priori and also to present personalized data. For example, cardiovascular risk assessment was performed with Framingham Heart Score. The Framingham score was based on population cohort and study and statistical analysis from a large amount of data set. And the idea of predicting non-eye disorder from your own fundus or from your own OCTA, it will give personalized data in order to refine medical strategy. And the idea behind all that is to add value to classical cardiovascular risk factors and to fine-tune existing risk score. In order to detect directly non-eye disorders from retinal imaging, I think that one technique is very promising, is the optic adaptative. Because with these exams you are able to have a look at very closely to the vessels, and you are able to analyze the wall of the arterioles, and I believe it will be a very interesting tool in the future. It is at the moment not very efficient for AI algorithm because acquisition is very long and you need a highly trained operator to perform these acquisition. But I believe it will be interesting in this research field in the future. Limitation of this study is we have to closely look at the methodological guidelines, Consort AI, Spirit AI, availability of retinal imaging in cardiology, general practitioner is something that we have to answer. We have to work on specific targeted population, and threshold, cutoff and binary variable were used in studies, but is it clinically relevant? Also, it is good to build AI algorithm, but it needs to be decision making. We have to now move on to RCT in order to prove meaningful outcomes, such as it decrease mortality, it decrease hospitalization. We have to answer the point of ethical responsibility, black box, and also cost efficacy of such strategy. The problem with retinal imaging in real life setting, it's the bad quality of imaging. And as a conclusion and perspective, I believe this is a very interesting research perspective to understand micro and macrovascular association. Retinal fundus photographs will be a good candidate, a good tool for future research, and we are now moving from proof of concept to clinical trial, and we need to go for research dataset to actual health clinical workflow. And just a slide to illustrate where I believe the retinal imaging in the non-eye disorder disease will take its place, so as a add value in order to get a more robust cardiovascular status assessment. And I thank you for your attention, and I'm available for any question. Thank you very much.
Good afternoon, ladies and gentlemen. Thank you, Professor Andrew Gray-Brosey, inviting me here. My name is Xiulan Zhang, came from Zhongshan Ophthalmology Center, ZOC, Guangzhou, China. I would like to discuss with you AI in glaucoma, present and future. I don't have financial disclosure. So far, in glaucoma research, AI algorithms mainly focus on two parts, diagnosis and prediction. When we're talking about prediction, it actually covers two aspects. One is to predict the biometric parameters from one imaging module to another. Another is about predicting the longitudinal change or the progression of the disease. Algorithms based on different imaging modalities have been developed. Look at the figure. The top three are fundus photo, OCT, and visual field. Let's see diagnostic AI. Study has shown that the AI based on fundus photo can perform well in detecting glaucoma suspect. Look at the curve. The AUC is gray, 0.9864. Also, the sensitivity and specificity are great too. A smartphone-based visual field deep learning system for glaucoma detection has been developed by my team. The video, let me show you the video. The video shows how the APP works. Download APP into your cell phone, scan PDF of visual field. With a couple seconds, you will tell you the risk of glaucoma. Our team also developed the first visual field plus OCT bimodal AI system to diagnose glaucoma. The bimodal algorithm defeated either single module algorithm and have a good generalizability in OCT data from different bench. Once more, my team also developed an ASOCT-based algorithm to detect narrow-angle suspect using AI. This is the first digital gonioscopy system, DGS, based on 3D swept source anterior segment OCT. It can rapidly differentiate between wide and the narrow angle. It can also able to detect extent of peripheral anterior synechia. It is a promising alternative to gonioscopy. Let's see predictive AI. Early prediction of disease progression may help to locate the individuals that do need early interventions. For example, patients that have a high risk of developing glaucoma should monitor their IOP more frequently. It can help to develop reasonable and rational treatment plans, such as glaucoma patients should have medication or surgery. He can avoid unnecessary treatments to save money and reduce side effects, such as if glaucoma patients have high risk of a failed trabeculectomy, they may choose their surgery. If prostaglandin doesn't reduce IOP sufficiently, they may choose other medications. There are some AI prediction algorithms in glaucoma research. Prediction refers to predicting future outcomes based on baseline information, such as fundus photo, OCT scan, and visual field. However, previous studies has major limitations. Sample size too small, no external validation. Our team developed AI algorithm based on fundus photo for glaucoma prediction. The model can effectively identify individuals at high risk of glaucoma onset or progression in the next 3 to 5 years. This paper was get published by JCI, and this is the first study to develop an AI algorithm for glaucoma onset and progression prediction. So far, the major limitation for glaucoma AI to diagnosis or prediction, AI algorithm cannot perform well trained with smaller dataset. It takes a lot of time to correct and label data. We need to explore how to develop high-performance AI with relatively small sample size data. We still need prospective study to validate the performance of AI algorithms. We still need to improve accuracy of their prediction. Prediction based on multimodal imaging and omic data may have better performance. On the other hand, AI is like a black box. We need to open it and reveal the hidden secret. So what should AI teach us? Let's see the future trend. Smartphones are everywhere today, and they have the potential to replace the basic medical devices. And they could be connected with the cloud anytime. Therefore, smartphones are excellent platforms for future telemedicine, such as some researchers have invented smartphone-based fundus photography and the visual field testing. And measurement based on these photos so far has a good correlation with that from medical devices. This is a pipeline for surgical face recognition, pupil detection, and the true activation in phaco surgery. In the future, we could develop more surgical AI algorithms for laser ocular surgery too. We believe that prediction based on multimodal imaging and omic data will have better performance to precisely predict the risk of incidence, the risk of progression, and the effect of the medications. However, in glaucoma AI, there are lots of challenges. We can separate two parts. One is in development, including relatively poor interpretability, data annotation, lack of external validation, and data sharing and privacy protection. The another part is in deportment, including acid bias, poor generalizability, quality control of obtained images. In the future, we need to overcome these challenges to produce more robust AI algorithms. Relatively poor interpretability. There's some way to improve interpretability. Awareness of interpretability issue at early stage of research. Proactive use of methods to increase clinical utility. And more exploration in interrogating the decision boundary. In my team, we use GrandCam to generate heat map to indicate the key region in glaucoma diagnosis and prediction. As you can see in this figure, the heated region align with their human knowledge in glaucoma diagnosis. Time and labor consumption of data annotation. There's some way to reduce time and labor consumptions. Unsupervised learning, more data sharing, and cross-regional cooperation. develops efficient semi-automatic data annotation tool. Lack of external validation. Using public data set, more cooperation with other researchers, stronger data protection techniques may help to get external validation data. Data sharing and privacy protection. The researchers has come up with many solutions to reduce the risk of data sharing and privacy protection, including development of clinical data exchange system, application of federated learning, and privacy-preserving artificial intelligence. My team established a public database of ophthalmic imaging eye challenge to promote the development of ophthalmic AI. It is currently the largest finely labeled public database of ophthalmic imaging, including the glaucoma, AMD, and higher myopia. Ethic bias. To increase the diversity of data sets, improved race ethnicity reporting, train on balance a representative data set, further validation among multi-ethnic groups, improved collaboration among worldwide centers can reduce the ethnic bias. Poor generalizability among different devices. Many ways to increase the generalization capability of AI on different devices. Train AI on data from diverse devices. Further validation among different devices. Standardize data from varied devices. And use appropriate reporting metric consistently and construct a multimodal algorithm. In my team study, we built a bimodal diagnostic algorithm. Both OCT and visual field are fed into the algorithm to predict if this is a glaucoma. The training data was based on DRI OCT from Topcon company. And in internal and external validation, besides DRI OCT, we use OCT images from circuits and spatulas. As shown in the ROC curve, the performance fell a little bit, but still good enough. Quality control of obtained images. This figure shows a framework of a quality control by AI. A deep learning system is used to classify if the slit lamp images meet the quality criteria. So let me conclusion. Glaucoma AI algorithms are booming. AI will sharply improve glaucoma diagnosis and prediction. Smartphones are the potential replacement of traditional devices in ocular disease diagnosis and monitoring. There are still multiple challenges to have to be overcome in the development and deployment of glaucoma AI. I would like to thank you, my iGlaucoma Cooperation Research Group, Professor Yu Qiao from Chinese Academy of Science, Professor Yanwu Xu from Baidu, Professor Minghui Tan from South China University of Technology, Professor Kang Zhang from Macau University of Science and Technology, and Professor Ting An and Daniel Ting from Singapore National Eye Center. And this is my team. So thank you very much.
Dear colleagues, now we have a time for a discussion. We are lucky to have nearly all of the presenters with us. Only Professor Pearse Keane could not be with us today. We wait for your questions on the chat, and in the meantime, we'll of course have some discussion between us. There are no questions yet, so I have a question. Well, let me start with the first presenter, Professor Michael Goldbaum. I'm not sure if he is present. Professor Goldbaum. I mean, he's logged in, but for any reason, he's not with us at the moment. Yeah, I would like to thank our presenters for great talks and very informative presentations at first. Well, so maybe I can ask Professor Xiulan Zhang. Do you know how many AI-based devices are registered in China, and if there are any oriented into glaucoma so far, regarding the topic of your talk? So I think you are muted, so maybe you need to switch on the microphone. Oh, yes.
Okay, thank you. The questions. Actually, in China, I think many people, I think China, including Hong Kong, including Taiwan, okay, and Macau. I know that so many people try to do many AI products in China, but as far as what I know right now, only my team can go there ahead. So we already have the intact algorithm for glaucoma diagnosis and prediction. For example, in the anterior segment, there are to detect the narrow and the open angle, I developed the digital gonioscopy system that is promising to replace the goniotomy in the future, I believe. And then I have the based on the visual field to detect the glaucoma, and also I developed the APP and the paper published in the Nature, the magazine, and then I developed the visual field plus OCT bimodal algorithm, so that increase the performance of the algorithm. Okay, and then I developed the prediction algorithm based on their fundus photo to predict the glaucoma incident and glaucoma progression in the next 3 or 5 years. So I mean, all these studies have been, the result have been published in a very good journal and was recognized by the world, I think. And also, I know.
Something happened. Xiulan, are you with us still?
The noise. I know that also some specific algorithm combine the retinal disease and the cataract and the AMD together to diagnosis. I think in China we have so many the algorithms have been developed, but just a few can go to the market, something like that, transformation. Okay, but my team already have one already get approved by the FDA. That algorithm is based combined with the AMD diagnosis. The glaucoma and AMD actually begin in the beginning together with the retinal diabetic retinopathy together, but FDA just approved the two, glaucoma and AMD. So this is the first one product for glaucoma diagnosis in China so far. Thank you.
So this is not, as I understand, registered yet, but it is under registration or just submitted for
registration? Already approved.
This is already approved. You're
yes.
algorithm in China.
Yes.
That's good. Thank you so much. I mean, yeah.
Yes.
Well, the Professor Goldbaum is with us. Michael, can you hear us?
Yes, I can hear you.
Yeah, so we know that in US you have already only 3 AI-based medical devices approved by FDA, and all of them are related with the diabetic retinopathy. Yeah,
Yes.
am I right? Or
well, I mean, that's not the area that I was prepared for. I mean, it was talked on the background, but
yeah.
yes.
So, well, but my question was because in Europe we do have also some algorithms for AMD, and well, the glaucoma is a bit more complicated. As a matter of fact, not so many algorithms are targeted into glaucoma. But the question is why other ophthalmic disease were not, let's say, approved by FDA. But well, maybe you are not.
I don't know what dealings are currently in the prospect for the FDA. There are, as you are aware, a number of areas of research, and it's in a quickly evolving field. But I don't know what has been finalized with the FDA on screening and in other diseases other than diabetes.
Yeah, I have a question to Louis. I mean, you nicely presented the let's say some new possible applications of ocular imaging to let's say cardiovascular risk disorders and so on. So, but how do you think we could have better access to the data set? I think that here the major limitation is that we don't have really a good, even as you mentioned, I mean, we are data factories today. I mean, all hospitals produce a huge amount of data, but for any reason, well, probably we are not very well prepared to collect, to classify this data. What should we do about that?
Thank you, Andres, for this very interesting question. Yeah, you're completely right. The problem is everybody is working on their own research unit, and it's quite difficult to get an access to one thing, a very big data set, but also a good quality data set. Because in my research area, you need, on the one hand, retinal imaging, so good retinal imaging, but you also have to get data about the cardiovascular status of patient, and it's very difficult to get good quality label data. So the idea for future collaboration and studies is to build open source data set with high quality retinal imaging, but also good label data about cardiovascular risk factors, cardiovascular background, and history. And I think we'll be able to work further in this area with open data source data set. And also we need for generalization to work with different device, different OCT, from Zeiss, from Heidelberg, Optiview, and so on, in order to make these algorithms not just for academic research, but also a good interest in clinical settings.
Thank you so much. I'm sorry, our time well for the discussion just ended. We need to move to another session. So thank you so much.
Thank you very much. It was really interesting.
Great.
Bye-bye all.
And yeah. Bye-bye.
Bye.
Dear colleagues, now we start the second session of our meeting. This session is on innovations, new applications of AI in ophthalmology. I will shortly introduce our speaker. The first is Professor Kerry Goetz from US, Associate Director at National Eye Institute, Office of Data Science and Health Informatics. Professor Goetz earned a master's degree in genetics and development biology from West Virginia University. She is an associate director. As this director, she coordinates existing activities within the National Eye Institute and across and provided needs for new trust agency programs in data collection, data sharing, and data interoperability. She works to accelerate scientific discovery, foster collaborative research, and ultimately improve public health through the application of scientific data and knowledge management in the eye health sciences. Her co-author is Professor Michel Hribar, also from US, from National Institutes of Health. And Professor Hribar, she is an associate professor in the ophthalmology and in the Department of Medical Informatics and Clinical Epidemiology, where she leads the ophthalmic informatics research groups at Cassie Eye Institute. Her National Institutes of Health funded research focuses on the effective reuse of electronic health record data for research in ophthalmology. The second the first talk will be on AI and National Eye Institute present and the future. The second talk will be delivered by Professor Kang Zhang, who will speak on EyeGPT, a large language model for clinical ophthalmology and eye research. Professor Kang Zhang is currently a professor of the Faculty of Medicine in Macau University of Science and Technology. He was previously a professor of ophthalmology and the founding director of the Institute for Genomic Medicine at the University of California, San Diego. He is particularly known for his work on nanosterile stem cell research, gene editing, and artificial intelligence. The third speaker will be Professor Jeoung, who will speak on explainable AI for glaucoma diagnosis. Professor Jeoung works at the Department of Ophthalmology in Seoul National University Hospital. The last speaker will be Professor Alvin Liu from US, who will speak on prediction of imminent conversion to neovascular age-related macular degeneration using multimodal data and ensemble machine learning. Professor Alvin Liu is a director in the Wilmer Precision Ophthalmology Center of Excellence at Johns Hopkins University, and his research interests include application of artificial intelligence in the screening, diagnosis, prognostication, and treatment of ophthalmic diseases with a specific focus on vitreoretinal diseases. Let's start the presentations.
Thank you for the opportunity to present AI at the National Eye Institute. My name is Kerry Goetz. I'm the Associate Director of the NEI's Office of Data Science and Health Informatics, and I'll be jointly presenting this with Michel Hribar, the NIH Data Scholar at the National Eye Institute. Neither of the authors have any financial disclosures. The National Institutes of Health is part of the U.S. Department of Health and Human Services in the United States. It is the topmost U.S. medical research agency and the largest public funder of biomedical research in the world, with a budget of over $45 million in 2022. The United States National Institutes of Health is over 200 years old and is comprised of 27 institutes, centers, and offices. The National Eye Institute is one of those 27. The National Eye Institute was created in 1968 by the U.S. Congress under the Johnson administration, with a focus on advancing national efforts in vision science. Since then, the NEI has become a world leader in directing and funding vision research with a fiscal year 2023 budget of $896 million. The NEI has a significant impact on public health and quality of life and on science. I'll just point out that the NEI has funded 8 Nobel Prize winners for their innovations that were initialized in the eye and vision system. Through the years, the vision system has proven to be an accessible setting for generalizable research. There are several notable artificial intelligence events from the NIH and the NEI in recent years. Starting in 2018, the NIH published a strategic plan for data science and established the NIH Office of Data Science Strategy. During the same year, the U.S. Food and Drug Administration, or the FDA, granted breakthrough device designation to the company IDXDR, which is an AI diagnostic system that autonomously diagnoses patients for diabetic retinopathy and macular edema using retinal images. This was the first AI-based diagnostic using retinal images ever approved for clinical use in the United States. The following year, the NIH Advisory Committee to the Director on Artificial Intelligence reported its findings. This group was charged to determine opportunities for innovative cross-NIH efforts in artificial intelligence and identify ways for these efforts to reach broadly across biomedical topics and have positive effects across many diverse fields, diseases, and research communities. They were also tasked with identifying mechanisms for the NIH to build lasting connections and collaborations between the computer and data science communities and the biomedical research community to establish ongoing interactions that push both fields forward. They were supposed to define approaches, including training mechanisms and creative career pipelines that the NIH could take to encourage computer scientists to work in biomedical research environments and to better train biomedical research in computer science-related disciplines. And lastly, to identify the major ethical considerations as they relate to biomedical research and using AI and related technologies for health-related research and care, and to suggest ways that the NIH can build these considerations into its AI-related programs and activities. So with that information, the NIH set ahead with a couple of projects that I'll describe in a moment, but the NEI actually took an approach to build off of these efforts by publishing its own strategic plan that included a cross-cutting area of emphasis in data science, as well as establishing the Office of Data Science and Health Informatics, which is the office that I lead. And even more recently, the NEI and the director, Dr. Michael Chang, have been committed partners and co-leads to data science and AI advancing efforts, such as the NIH Bridge to Artificial Intelligence Program, or Bridge to AI, and the Artificial Intelligence Machine Learning Consortium to Advance Health Equity and Researcher Diversity, otherwise known as AIM Ahead. In the next couple of slides, I'll describe a little bit more about the data science component of the NEI strategic plan, Vision for the Future, which aims to span our research directive from 2021 to 2025. The new NEI strategic plan adds cross-cutting areas of emphasis to the domain-specific topic areas that NEI has traditionally focused on. Scanning the QR code on this slide will take you to a website to access the entire plan. As you can see, the data science area accompanies other topics such as quality of life and regenerative medicine. The data science chapter specifically focuses on laying out the NEI strategy for ensuring that vision research remains a leading force in artificial intelligence. Part of the strategy to realize this goal comes from optimizing data management and data sharing and ensuring that the proper safeguards and ethical protections are in place. The data science chapter reflects on the access to large-scale multimodal data that is available for biology, including all of the omics, imaging, which capitalizes on the ability to image the inside of the eye non-invasively, clinical data, including electronic health record data, and public health data, which encompasses social determinants of health. But there are still many hurdles to overcome. For example, individual diagnosis of disease is complex and requires AI to integrate clinical findings, imaging data, and multiple diseases. So far, artificial intelligence has been well-performing on narrow tasks, but performance drops significantly when incorporating complex inputs such as these. Second, there is still a lot of work to be done related to generalizability based on population factors, in addition to image device differences and real-world data quality. And lastly, there's an unclear ground truth to use for training models, since diagnoses are highly variable and an individual's experience exists on a disease spectrum. Compound that with the non-uniform diagnostic coding and labeling that exists in most data sets. For example, the terms moderate or rapidly progressive glaucoma can be highly subjective. So what we need is more collaborative data sharing and harmonization. Modern data-driven research relies on standard representations of data across multiple studies. The NIH implemented a data management and sharing policy for all funded activities in January of 2023 that requires a data management and sharing plans across those studies. And the White House Office of Science and Technology Policy circulated guidance that is set to take effect in 2025 that requires all federally funded research to be available openly without an embargo period. But we view these policies mainly as sticks, and we also want to create incentives or carrots at the NEI to encourage sharing. One activity toward incentivizing sharing is a new publication type for data sets through the TVST journal led by Marco Zarbin, Pearse Keane, and Aaron Lee. And our NEI Office of Data Science, including myself and Michelle Hribar, along with Dr. Sally Baxter, have also been actively engaged in incentivizing the uptake of the OMOP Common Data Model, which Michelle will talk about more in upcoming slides. The NEI also recognizes that there is a significant need for standardization in ocular imaging, since it is the basis for many AI advancements. The trouble is that both clinicians and researchers struggle to exchange and retrieve imaging data from devices based on proprietary image standards. To address this concern, the NEI, the Department of Health and Human Services Office of the National Coordinator, and the US FDA hosted a workshop that brought together key opinion leaders to outline a path forward toward interoperability. Since then, the FDA has recognized the image standard DICOM as a preferred standard for ocular imaging devices and for vendor conformance labeling. The American Academy of Ophthalmology and ARVO also published a joint statement of support stating that the time is now for non-proprietary image exchange. So now I'll turn it over to Michelle for the rest of the presentation. Thank you.
Hello, my name is Michelle Hribar, and today I'm going to be talking to you about the efforts that the National Eye Institute is making in increasing access to data that will be used for AI. There's a couple different efforts, and the first one I'll talk about is making observational EHR data more interoperable and available. In the United States, most of our EHRs that are in academic medical institutions or large healthcare systems have about a decade's worth of EHR data, but that data isn't very available beyond the single site. There have been many research projects that have used observational health data or real-world data from a single site or a handful of sites, but it can be very difficult to do research on from multiple sites because the data just isn't standardized and it's not interoperable. And that means that in one institution, your data element may be named one thing, in another institution it's named another. And sometimes it's because you have different EHRs. Sometimes it's just because institutions have the same EHR, but they just implemented it differently. One way to improve interoperability is to use a common data model. And we have been working with Odyssey Group, which is Observational Health Data Sciences and Informatics, and they manage the common data model called OMOP, which is Observable Medical Outcomes Partnership, that was developed over 10 years ago, and it was a public-private partnership between the FDA, industry, the NIH, and academia. And the data model is just a common way of naming and conventions for storing clinical data in the EHR and in claims databases so that it can be easily reused. And the Odyssey network is rather impressive. It has thousands of collaborators in over 80 countries, and it has produced hundreds of studies and publications. Now, ophthalmic eye data, especially data that has been collected during clinical care for the eye exam in your EHRs, is not part of the OMOP Common Data Model yet. So we have been working on standardizing that data so it can be included in the OMOP CDM. We did this through forming a work group called the Eye Care and Vision Research Work Group. It is open for anyone to be a member, and we have members from all over the world who are working towards improving the standardization of this data so that it can be included in the OMOP CDM and can help make this observational data more available for research. Other efforts that the NEI is focusing on is actually creating prospective data sets, since these data sets will help avoid the bias of observational data that's stored in the EHR. If we only use AHR data sets for AI and for data discovery, we're only going to be potentially including a subset of the population, particularly since we know there are a number of particular subgroups that are not well represented in healthcare or don't have great access to healthcare. So there's a couple of different initiatives that the NIH is focused on and that the NEI is part of. The first is Bridge to AI. This was funded by the Common Fund, and the idea is to build large data sets from multiple sources and to use standards for the data collection and storage so that it is interoperable and reusable. And it is very well funded. It is over $130 million over 4 years, and it contributes from multiple institutes, including the NEI. The important thing about this data project is that it's not hypothesis driven like most of the NIH data projects. The idea is just to create the data set, and then future research studies will propose research questions and hypothesis about the data and use the data for those types of scientific studies. The second is Aim Ahead. This is run by the Office of Data Science Strategy, and this is really trying to address the challenges of health disparities in minority health by creating diverse data sets. And it's focusing on efforts of trying to detect bias and improve bias in this data. And this is also very well funded, over $100 million for 2 years for centers who are working on this. And this is work that is done through the Office of Data Science Strategy, and that's run by Susan Gregaric. Another project for building AI-ready data sets is the All of Us research program. This dates back to 2015 with an announcement from President Obama at the time. And the goal was to collect a diverse amount of data about 1 million Americans with deliberate oversampling in underrepresented patient groups. Now, this has been going on. There's data that's available now, and you can get access to it in the research workbench, but it doesn't yet include ophthalmic data in imaging. So we are working with, the NEI is working with the All of Us research program to include that data and imaging, and hopefully that will be available in the next few years. And this is also a very well-funded project. I'd like to highlight one of the Bridge to AI projects, since it's actually being led by a couple of ophthalmologists, Drs. Aaron and Cecilia Lee from the University of Washington. And this is one of those projects that's creating a non-hypothesis driven data set. And they are collecting a triple balanced prospective data set of 4,000 diabetic patients. It's balanced for race, gender, and diabetes stage. They're and they're collecting over 15 unique data types about these patients. The project itself includes over 50 researchers from 8 different institutions, and it's managed at the University of Washington. We're very excited about this data set because it will include ophthalmic eye data and imaging. Now, in order for us to be AI ready in medicine, and particularly in the ophthalmic sciences, we need more than just data. And so we also need medical education in AI and data science, not only for building models, but for helping to understand how they be used and to help understand the data that fuels them. Now, the only tool that's used by every clinician and scientist is actually the EHR, but there's really no systematic training or framework about that uses or the implications of that technology, not only on clinical care, but on research and AI models that might be derived from them. And it's really unlike a lot of the other clinical skills that are taught. For example, a lot of when you learn how to use the EHR, it's often just an apprenticeship. You're learning how to use it from senior mentors who may not be as well versed in how to use the EHR effectively, but also how to enter data in a way that the data can be reused effectively. So, for example, we find that trainees are very well trained in how to code diagnoses, for example, for billing, but not necessarily realizing that they're not entering very much structured data about their patients in the EHR. So it can be difficult to get accurate structured data off the back end to use for AI models. Also, the thing that's important to understand that's sort of missing is that this technology, EHRs alone, but also, once we're adding AI and more, sort of smart clinical decision support tools, they're really fundamentally changing the practice of medicine. And we've already been part of this for a while. So, the way that perhaps our parents' generation practiced medicine is quite a bit different the way that it's practiced today. There's a lot more available imaging, quantitative tests, and so really trying to figure out how to make the most effective use of this data, whether it's coming from a quantitative test or you're getting some sort of recommendation from an artificial intelligence model. And this is a very popular subject of study in informatics, but also in ophthalmology as well. And I'll talk a little bit more about those efforts in ophthalmology. So one of these implications for technology is its potential for improving delivery and access to care. And telehealth and AI refers to the remote delivery of care, being able to be in one spot while your patient is in another, and still being able to provide care or clinical judgments. This trend became almost necessary of going from real to virtual during the pandemic. We experienced in all aspects of our lives during the pandemic where, we were getting a lot of our entertainment and communication via virtual, Zoom meetings or accessing streaming services, for example, instead of going to a movie in person. But it also was the same for healthcare. Now, in order to see patients, they had to be seen, virtually. And but we really need to be careful about evaluating the limitation of telehealth, making sure that it's, it's cost effective, that it's actually accurate in providing the best quality of care, and that we're really trying to develop new and reusable models for remote care that can be, scaled and used by multiple people and they're robust. But we also have to be careful that by doing this is a great opportunity that we're not actually exacerbating disparities in access to care. If we are, for example, making this technology a prerequisite for accessing care, then we might be eliminating some parts of our population. So we really have to understand the social determinants of health, how they're related to telehealth, but also to vision disease and eye care. What is the best way for us, given the tools that we have, to improve that access for these patients and to really see what that impact on preventable vision loss could be. And there are many active projects on this, and also looking at these different disparities and trying to figure out the best way that we can provide and find all the patients that need care and make sure that they receive that care. Now, another aspect of this, and this is something we hear a lot from our clinicians, is that, well, this is all well and good, but I already have trouble with the EHR and it's a pain. Now you're telling me I have to add telehealth services. I'm now going to be incorporating AI models, and I already don't know how to use my EHR very effectively. And at OHSU, we've done several projects looking at documentation. And so, for example, we found that, the notes in ophthalmology are very long. I mean, they're about 2 to 6 pages. The content is heavily redundant. It can be up to over a quarter of the note is generated from the previous visit's notes. And this is increasing trend over time. And so we really need to be careful about, what we do in the EHR, both for, reducing this burden of documentation, making it accurate, making sure that it actually helps clinical care. It's not getting in the way by, making these bloated notes that no one actually winds up using. Can we do something that takes less time and is more effective for clinical care, and that could actually have better data on the back end that could be reused? Because right now, with these bloated notes and a lot of the data not in structured fields, we can't really reuse this data very easily. So in conclusion, we just have some thoughts that we'd like you to think about as well, about what this transformative impact is on ophthalmology and vision science moving ahead. We all know that we're going from what once was maybe a more qualitative type clinical care to very quantitative. And, as we start integrating more imaging, more AI into our practice, what is the added value for clinicians? We know engineers will help continue to develop these methodological advancements, develop these solutions that can really help generalize and provide access to care, and improve data standards and interoperability of data. But clinicians really have to be thinking about, what is the best use of AI? What are the clinically relevant questions? Where can AI help? And where can it really not? And that's almost as important of a question, to really be thinking about what it shouldn't be doing and what are the things, what's the value added of the clinician in the clinical visit, and really focus on training for that and making the most effective use of AI for the tasks that AI is really well suited for. We'd like to thank you for the opportunity to talk with you today, and we'd encourage you to contact us with any comments or questions. You can reach Kerry Goetz at the NEI at her email address there. She is the Associate Director of the Office of Data Science and Health Informatics. You can also reach me at my NIH email, because right now I am working as a data scholar. That's a temporary position, but I am still working a little portion of my time at my home institution at Oregon Health and Science University, where I'm a faculty member in ophthalmology and medical informatics. Thank you.
Hello, I'm Professor Kang Zhang Today, I will give a talk on building world-class eye research and innovations in the big data and AI era. As all of us know, major challenges in eye delivery and therapies include challenges in existing delivery pattern systems. This includes the data challenges, technology challenges, and the population challenges, including untreatable blind disease such as glaucoma and genetic eye disease, common eye diseases such as macular degeneration, diabetic retinopathy, uncontrolled myopic pandemic, etc. So today I'm going to discuss several topics, including the first developing tools and including omics and then mostly talk about AI with regard to foundation models in transfer learning and AI physician interactions and trust. Recent breakthroughs in using primary protein sequence to predict the three-dimensional protein structures have revolutionized structural biology. In this case, DeepMind has proposed the AlphaFold 2 and is being used for accurately predict three-dimensional protein structures. And we have been working in this space, including using structure predictions to predict ligand receptor interactions. In this paper, we were able to predict the ligand receptor interactions of BDNF and its track receptor. In addition, we're able to design small molecules that specifically target those binding sites. In addition, we're able to, using our own developed keystone fold, to predict a class of proteins that is involving diverse, important biological processes such as aging. This elongation of long-chain fatty acids, or ELOVs, are a family of proteins, and we're able to predict all their three-dimensional structure, as well as we're using the genetics in combination with these protein structure designs to predict and develop new drugs for treating cataracts. Now I'm going to turn into using electron medical records and big data and AI for delivering healthcare and improving outcomes. As all of us know, one of the challenges in applying AI is electron medical records information rapid growth, and they're containing diverse and complex digital health data, such as digital photographs of the eye and chest x-rays, ERGs, CTs, chest x-rays, etc. And there are also other challenges, including uneven distribution of the healthcare resources. In this review, we summarize the important issues in implementing artificial intelligence technology in medicine, including how to apply to different areas, including diagnostics, therapeutics, population health management, and administration. In particular, we think that how to integrate healthcare information, especially patient care information, with the patient, hospital, physician, as well as regulatory bodies are going to be key in developing the technology. Now, I'm going to give you some examples how we use AI to assist physicians in making good diagnosis. In this case, I'm coming back to the eye, and in this first case, we're using transfer learning to learn from large common data sets such as ImageNet to carry out specific tasks of eye diagnosis and pediatric disease diagnosis, in which we first train the CNN in tens of millions of common images, and then we use the framework to trained with much less data, namely hundreds of thousands of optical coherence tomography images for diagnosis of a CMV, DME, Jeoung, or normal OCT images. In the second case, we will further transfer learning in this pediatric disease category, namely pneumonia. We're able to differentiate pneumonia versus non-pneumonia and bacterial pneumonia versus viral pneumonia. And then obviously we achieved very high accuracy, and the performance is comparable to a mid-level US retinal specialist. I'm sure by further large amount of the data training, we should be able to achieve and surpass senior retinal specialist level. Again, in this case, we're able to use an occlusion test to specifically label the lesion site, as well as using the OCT to automatically guide the treatment strategies. In the second case, we're able to use AI to gain new knowledge and diagnostics paradigms. In this case, we're using fundus photographs to diagnose systemic diseases. And we're talking about in diagnosing chronic kidney disease and type 2 diabetes from retinal fundus photographs. Here we used over 110,000 retinal photographs utilizing deep learning and as well as demographic data to predict precisely not only the detection of chronic renal disease as well as type 2 diabetes, in addition to the onset or incidence of future predictions of incidence of both diseases. We'll also be able to predict some key parameters of the two diseases, including the glomerular filtration rates, as well as fast glucose level. Taking advantage of this type of future detection technology or prediction technology, we apply further to predict the future onset of glaucoma, as well as the severity progression of the glaucoma. This is in collaboration with Dr. Xiulan Zhang from Zhongshan Ophthalmic Center. We're able to also use the same technology, namely transfer learning and other technology to diagnose COVID-19 pneumonia using computed tomography. I won't go into the details. And obviously, what I told you now is using computer vision to diagnose disease based on images. However, as all of us know, that most of the electromedical records are comprised of texture data. So we will need another type of technology or artificial intelligence to extract and organize those data. This is called natural language processing. And in this paper, we're one of the first to use this technology to evaluate pediatric disease. Here, we first labeled 50,000 pediatric electromedical records, and then using deep learning as well as natural language processing to formulate and extract 1.3 million raw data. This in combination with a library of packs as well as other data to formulate fully structured data sets, then undergo classifications. And in this case, we were able to give and obtain very high classifying accuracies. And this is comparable to a mid to senior level pediatrician level. Up to now, I was telling you about the application of artificial intelligence in medical records. obviously all of us are also going to use another side of data, which is multi-omics data. So here I'm going to talk to you some of the approach we're taking. In 2006, we're the first to use in genome association study to identify a major gene for macular degeneration called HTRA1. And this gene particularly play a key role or predominant role in predisposing Asian population to macular degeneration. In addition, we'll also be able to identify specific genes for specific subtypes of macular degeneration, in this case, geographic atrophy. Along with the International Genetics Consortium, using 30,000 AMD cases and 100,000 controls, we're able to identify all of the common variants for macular degeneration. This includes CFH, HTRA1, C3, and C2. And using those data, we're able to construct a risk profile for the entire population. Namely, if a person is homozygous for HTRA1, C3, CFH, and is a smoker, the chance of having macular degeneration of this patient is extraordinarily high, namely 500 to 1,000-fold higher than non-homozygous, non-smoker individuals. So let me summarize what I talked about to you. Obviously, we will having challenges in applying artificial intelligence in medicine, particularly in ophthalmology, including the existing delivery patterns and data challenges, technology challenges, population challenges. However, they also give us a lot of opportunities, particularly in China, including developing new eye drugs and therapies and the new ophthalmology guidelines in China. And obviously, there are also other important opportunities in building an ecosystem of excellence in collaboration and synergy with other colleagues of us, including endocrinology, brain science, and the geriatrics. I want to thank you for your attention.
Thank you, Chairperson, and thank you all for having me at this AI in Ophthalmology conference. I am Jeoung from Seoul National University Hospital, Korea, and today I will be talking about explainable AI for glaucoma diagnosis. This is my financial disclosure. I have no financial disclosure in my presentation. Glaucomatous optic neuropathy refers to the selective loss of axons and death of retinal ganglion cells, leading to visual field defects. Glaucoma can be assessed through the structural and functional tests such as optic disc photography and visual field examinations. According to the biomechanical theory, the lamina curvosa, a structure in the eye, plays a significant role in glaucoma pathogenesis. Increased intraocular pressure causes the lamina curvosa to displace posteriorly and become thinner. In our recent study, we focused on measuring the curvature of the lamina curvosa using OCT scans. We observed significant deformation in the lamina curvosa of normal tension glaucoma eye and primary open-angle glaucoma eye compared to healthy eyes. This illustration shows a significant lamina curvosa deformation in normal tension glaucoma eyes. Moreover, in high tension glaucoma eyes, this slide shows more significant deformation and posterior displacement of the lamina curvosa. Now let's move on to the next topic, artificial intelligence in glaucoma. Artificial intelligence is the simulation of human intelligence in machines, programmed to think like humans and mimic their actions. Machine learning is computer algorithms that improve automatically through experience, built on mathematical model based on sample data, known as training data. Deep learning is a class of machine learning algorithms based on neural networks that permits a machine to train itself to perform a task. Machine learning algorithms typically require structured data, while deep learning networks rely on layers of artificial neural networks. In our clinic, distinguishing between glaucomatous and non-glaucomatous structure changes is challenging, even for well-trained ophthalmologists. Deep learning classifiers can assist in discriminating between glaucomatous and compressive optic neuropathy. We included OST images from glaucoma and compressive neuropathy cases and evaluated the performance of a deep learning classifier in differentiating between these two conditions. Let's look at this case. This case displayed advanced cupping, severe new retinal rim thinning, and diffuse RNA atrophy, which could have been misclassified as advanced glaucoma. However, the deep learning model predicted a relatively low probability of glaucoma. Further investigation through brain MRI imaging revealed a diagnosis of supracellular meningioma in this case. Our study demonstrated that the deep learning classifier accurately distinguished between glaucomatous and compressive optic neuropathy, surpassing the performance of clinical diagnosis parameters. Now let's turn our attention to the second topic, predicting function loss from fundus photographs using deep learning models. These are optic disc photographs. We asked ourselves, can we predict functional loss from monoscopic optic disc photographs? In our recent study, we utilized the deep learning algorithm to predict mean deviation from these photographs. We used a deep learning algorithm to predict mean deviation from monoscopic optic disc photographs. A total of 1,200 image pairs were included in this study, which were divided into training, validation, and testing sets. This division allowed us to evaluate the algorithm's performance accurately. These are healthy and early glaucoma eyes. In the images of healthy and early glaucoma eyes, heat maps revealed highly activated areas on the optic disc photographs. The algorithm accurately predicted the mean deviation value and the probability of glaucomatous visual field defects. Trained deep learning algorithm demonstrated excellent performance in distinguishing glaucomatous visual field defects. It successfully quantified the mean deviation, showing a strong correlation with measurement and good agreement. In summary, our study demonstrates the potential of using deep learning models to predict functional loss from monoscopic optic disc photographs. These algorithms' accuracy in determining mean deviation and identifying glaucomatous visual field defects highlights its effectiveness in assisting with early detection and monitoring of glaucoma. Now let's move on to the main topic, explainable AI in glaucoma. In the traditional machine learning, there is a concept called the black box, where even the designers of the AI cannot explain why it arrived at a specific decision. Explainable AI, on the other hand, refers to artificial intelligence in which humans can understand the decisions or predictions made by the AI. This slide illustrates the difference between a black box model and explainable AI. With explainable AI, we can comprehend the decisions or predictions made by the AI. Our recent paper, titled Explaining the Rationale of Deep Learning Glaucoma Decisions with Adversarial Examples, we explored the concept of adversarial explanation. This paper and this study was done by Professor T-Ho Park in our hospital. These are the example pictures. Negative adversarial examples involve decreasing the cup-to-disc ratio, while positive adversarial examples involve the increase the cup-to-disc ratio. We repainted the imaging until the model classified it as either completely pathologic or completely normal. Pathologic examples were considered positive, while normal examples were considered negative. The application of adversarial explanation yielded significant findings. Negative adversarial examples exhibited a lower cup-to-disc ratio and a lesser extent of RNF defects, suggesting a healthier optic disc. On the other hand, positive adversarial examples demonstrated increased cup-to-disc ratios and clear retinal fibrillary defects, indicating glaucomatous changes. In another case, we observed a less clear RNF defects in the negative example, while the positive example exhibited a more distinct RNF defect. In our study, adversarial explanation increased the explainability of a GradCam, a conventional heat map-based explanation method. Adversarial explanation may help medical professionals understand more clearly the rationale of deep learning models when using them for clinical decisions. In summary, talked about the artificial intelligence in glaucoma. Deep learning classifier accurately discriminated glaucomatous and compressive optic neuropathy better than did clinical diagnostic parameters. And predicting function loss from fundus photographs, deep learning algorithm great feasibility for prediction of mean deviation and detection of glaucomatous function loss from optic disc photographs. Today, I talked about the explainable AI. Explainable AI is artificial intelligence in which humans can understand the decisions or predictions by the AI. By using the explainable AI, adversarial explanation may help medical professionals understand more clearly the rationale of deep learning models when using them for clinical decisions. Thank you very much for your attention.
Good morning, everyone. My name is Alvin Liu. I'm a retina specialist from the Johns Hopkins University Wilmer Eye Institute. I would like to thank the event organizers for inviting me to speak here today. And the topic of my presentation is predicting imminent conversion to neovascular AMD using multimodal data and ensemble machine learning. I do not have any relevant financial disclosures. Age-related macular degeneration is the leading cause for central vision loss in patients over the age of 50, and the vast majority of AMD patients lose vision due to the neovascular form. Historically, AREDS criteria have been used to provide average risk assessment for converting to wet AMD or for progressing to advanced AMD over the span of 5 years. AREDS criteria can be calculated from either clinical examination or color fundus photographs, and relevant biomarkers include the size of the drusen and the presence of pigments. The advent of optical coherence tomography, OCT, had vastly advanced our understanding of AMD. Specifically, now we know that there are various OCT biomarkers that are risk factors for converting to wet AMD or for progressing to advanced AMD. And these biomarkers include subretinal drusenoid deposit, hyporeflective core of drusen, and intraretinal hyperreflective foci. With the rise of OCT and the rise of artificial intelligence in the form of deep learning, these are the questions that we set out to ask in the current research project. Number one, we would like to know whether we can use deep learning to predict imminent conversion to wet AMD using OCT volumes alone. Number two, we would like to find out whether adding tabular clinical data improve our predictive power. And number three, how do we combine imaging data and tabular clinical data into a single predictive model? Next, I'd like to provide for you some information on our data set. Our data set contains over 2,000 patients and over 33,000 OCT volumes. 63% of our patients were female, and the majority of our patients were white patients. The mean age of our patients was 78.9 years. Our dataset only included OCT volumes acquired by the Heidelberg platform, and all of the OCT volumes involved had at least 25 line scans. In terms of the clinical tabular data that were considered, we included age, sex, visual acuity, and fellow eye status, meaning at the time of OCT imaging, whether the fellow eye had converted to wet AMD or not. Our data was split into 70% training, 20% validation, and 10% for testing. Data partition was performed on the patient level. In terms of the ground truth for converting to wet AMD, we defined the date of the first anti-VEGF injection as the conversion date. However, all the patients and images in the holdout test set were manually cleaned and verified for accuracy. The deep learning network backbone that we used was a 3D ResNet 50, and the best model parameters were selected based on the best balance accuracy during validation. In terms of classical machine learning models, we use random forest and XGBoost. Here's a schematic representation for how we incorporated the OCT imaging data and tabular clinical data into a single model. So first, we took the OCT volumes and trained a 3D convolutional neural network with these OCT volumes. And then we used two different ways to incorporate the imaging data with the tabular clinical data. As demonstrated on the right-hand side of the figure, we first extracted the feature vector of the second to last hidden layer in the CNN, and then used the feature vector as one of the variables for prediction in the classical machine learning model. And as demonstrated on the left-hand side, the image features in the last hidden layer of the deep neural network were linearly condensed and combined with the 4 clinical features. These were then further reduced using a dense layer for the ultimate binary predictions. Next, I would like to share with you the performance of the different models that we trained. In terms of predicting imminent conversion within 6 months to wet AMD, the top 2 performing models were the multi-layer perceptron model that used multimodal data, and the neural network that used only OCT volumes for training. Next, we performed a subgroup analysis and looked at the performance of the different models in predicting first eye conversion. As you can see, the top two performing models were the same as the previous slide. However, in this particular scenario, the multi-layer perceptron model that used multimodal data did indeed outperform the deep neural network that used only OCT data for training. In order to gain insight into what exactly our model learned, we performed class activation mapping analysis. And in the following slides, I'm going to provide two examples. Both of these examples were correctly predicted, and both of these eyes converted to wet AMD within 6 months of these particular images. So as you can see here, the area highlighted in this particular image corresponded to an area of shallowly elevated pigment epithelial detachment. Similarly, in this image, the area highlighted is an area of shallowly elevated pigment epithelial detachment, also known as the double layer sign. And this is certainly encouraging because we do know that the presence of a double layer sign is highly correlated to the presence of a subclinical CNV, thus indicating that our models were likely learning from medically relevant biomarkers. Next, I would like to summarize our finding. Our most robust models achieved an AUC of 0.75 in predicting imminent conversion to wet AMD within 6 months on an eye level. Of course, at any given AUC level, one could set different sensitivity and specificity thresholds to suit different clinical needs. It appears from our results that adding tabular data to model training improved our model's performance in predicting first eye conversion. These predictive models could be used to personalize care for patients with dry AMD. For example, if a particular patient is predicted to be at a high risk of converting to wet AMD within 6 months, then this particular patient could be monitored more closely, seen more frequently in a clinic, or prescribed at-home monitoring devices such as at-home OCT machines. On a population level, these models could also be used as screening tools at a non-ophthalmology setting. In terms of future directions, there are 3 different avenues that we plan to pursue. First, we plan to incorporate deep learning segmented biomarkers such as intraretinal hyperreflective foci and subretinal drusenoid deposit into our model training. Second, all the deep learning models that we presented in the current study used convolutional neural network as backbones. As the next step, we also plan to use vision transformers as the model backbone instead. Third, we plan to perform federated learning to update and train and retrain our current models using datasets from different institutions and using OCT images from different OCT platforms.
So now we start the discussion. I would like to thank all the speakers for great presentations. And of course, encourage our audience to put the questions on the chat. But in the meantime, maybe I would like to start with the topic that was brought by our colleagues from the National Eye Institute, that maybe we need to target on a particular research. So the first question, what finally, or what do we need? What kind of research now we need? Because to introduce AI into practice. Well, let's start with the ladies, and then, of course, I'll be happy to listen to opinion of our male colleagues, Alvin and professor from Korea, Jeoung. Yeah.
I'll kick it off, and then Michelle can add her comments. From the National Eye Institute, we're usually funding biomedical research a lot of times through clinical trials. And so what we're really trying to do is make sure that we're bridging those two things. Clinical trials are usually described in structured ways according to case report forms and using inclusion, exclusion, and outcomes measures. And we want to make sure that those closely represent real world observational data, which is why we're spending so much effort to map terminologies to the OMOP common data model and things like that. So we just want to make sure that whatever we're doing and funding actually has translational value.
Yeah, and I can extend that a little bit from an informatics perspective. And I'm working right now as a data scholar at the National Eye Institute, but that's a temporary position, and I'm normally an informatician at Oregon Health and Science University. And I know in informatics, a big challenge is that translational piece. And a lot of the standardization work that we're doing within the National Eye Institute will help with that as well. It's one thing to create a model and show that it works, but then trying to actually implement it at the point of care, especially if it's something that will be triggered by the electronic health record, requires having standardization of data, phenotypes, and those kinds of things, which is what we're tackling.
Alvin? What is your opinion?
Sure. I think I will take a step back and probably talk about two, I think, big trends that's happening in our field right now, and two key issues that we as a group should try to figure out. The first one is the issue of data. As we all know, the current generation of artificial intelligence, deep learning, it's primarily driven by data. So around the world, there are a lot of efforts to get as much data as possible. Right now, in our group, this particular group at our meeting are primarily representatives from the academic world and affiliated with universities. However, the other big player in the data field right now, it's actually private companies. At least in the US healthcare market, there are many, multiple startup companies that have amassed a huge amount of data in terms of hundreds of millions, and these companies are valued at billions of dollars. So the question is, how exactly do we, as in people who work primarily in academics, work with these big data companies to figure out a path forward? And the second big trend, it also relates to research, but on the more practical side. From today's talk, we are all very excited about all the advancement when it comes to research and modeling, stuff like that. But I think ultimately, our field will have to pay more attention in demonstrating that these models do improve outcomes, and maybe even better, demonstrate that we improve outcomes in a cost-effective manner. Because ultimately, if we cannot demonstrate that these technologies improve patient outcomes, the development in AI will not be sustainable. At least the payers may not be willing to pay for them.
Thank you, Alvin. Yin, would you like to comment on that? but you are muted. Oh, yeah.
Hi, everyone. My name is Jeoung from Seoul, Korea. I agree with all comments, and I'm a glaucoma specialist, and I think that we are currently using the AI technology, and based on the big data technology, we can make more correct diagnosis, and we can make more have more correct prognosis predictions. So based on this big data and AI technology, we can be able have more correct diagnosis and prognosis prediction.
Thank you. We have a question from the audience. The question is, in the context of preparing good data sets, are there any recognized methods for structural reporting of fundus images, taking into account structured vocabularies of changes observed in the image? Alvin, do you have a comment on that?
Sure. To provide a little bit of background, Michelle in her talk mentioned AI Ready. So both Michelle and I are part of that Bridge to AI project. And one of the leaders, Aaron Lee from the University of Washington, has been very involved at the level of the Academy, American Academy of Ophthalmology, to talk about the standardization of imaging, which is very important. And I think the main issues we're facing right now is, for the most part, most ophthalmic imaging platforms are made by commercial companies, and they always like to protect their proprietary technology. So a lot of times, the images generated by the different platforms, even within, let's say, the same imaging modality, OCT, can be different, and they don't talk to each other. So there is a major effort happening in the US right now, and definitely at the level of the Academy, to try to address this issue.
Thank you. I have a question for Michelle and Kerry. I mean, you presented also the works you started at. Well, you plan for increasing the data, the number of data sets in the US. Will these data sets will be also because you mentioned that they will be public, available for non-US, let's say, users? This is the first question, and the second, do you see any possibility for a let's say international collaboration, because of course we can also somehow help in establishing such a data set as a group of people all over the world, I mean different parts of the world.
So in general, I would say the National Eye Institute, when creating data sets for public use, tries to make them as broadly available as possible. So internationally, with commercial entities, we try to leave those avenues open, although sometimes, there are different user agreements that we have to have signatories on. My experience with creating international data sets can sometimes just be getting countries to agree on certain data being shared among partners. But that kind of speaks to the advantage of using like the OMOP Odyssey Common Data Model, is that data doesn't ever need to leave the source, right? We can have collaborative data research networks that can leave the data in their own environments. And so I think that has a real advantage in getting past some of these international political elements that we have little control over. I don't know if Michelle wants to add anything to that.
Yeah, and I think I just want to mention that the OMOP and Odyssey network right now is an international collaboration with pretty significant participation from Europe and Asia, as well as the US, and it's expanding everywhere. They're actually even trying to figure out how it can expand possibly to all continents, but right now it's just the 6 continents. So I think there's lots of opportunity for participants around the world internationally to get involved in this type of standardization work. And especially if your institution is part of this data network, then that will make it easier for you to access data at all other data partners within the Odyssey network.
Thank you so much. Unfortunately, we need to finish the discussion because the next session is coming. So thank you again for great presentations and for being with us during this part of the conference. So thank you so much.
Thank you.
Bye-bye. Dear colleagues, now we start the session number 3, practical implementations of AI in ophthalmology. And my pleasure is to introduce the speakers from this session. The first is Professor Paweł Strumiłło from the Institute of Electronics, Łódź University of Technology in Poland. And he will speak on presentation of the environment for the visually impaired. Then Dr. Sheila Zhang, who is the head of tele-ophthalmology department in Sankara Netherlands in India. Dr. Sheila Zhang is currently head of the as I mentioned, Department of Tele-Ophthalmology and E-Learning. She conducted many tele-ophthalmology workshops in India and abroad to teach and train medical and non-medical staff to implement tele-ophthalmology. The third speaker is Dr. Kai Jin from China, who will speak on artificial intelligence aided FFA images, interpretation, and clinical evaluation. Dr. Keane has received the MD and PhD degrees in ophthalmology from Jeoung University in 2018. In Hangzhou in China. He is currently a professor and ophthalmologist in the Department of Ophthalmology, the second affiliated hospital at the same university. His current research interests include diagnosis and treatment of retinal diseases, epidemiology, translation, and clinical research in ophthalmology. And the fourth speaker, it's Professor Haoyu Chen from China, who will speak on uncertainty-inspired open set learning for retinal anomaly identification from joint Shantou International Eye Center, Shantou University, and the Chinese University of Hong Kong. Let's listen to the lectures now, please.
Welcome. My name is Paweł Strumiłło. I work at the Institute of Electronics, Łódź University of Technology, and today I would like to present you the work we have been recently done on assistive technologies for the visually impaired. This is the scope of the work we carry out in our institute. As you can see, we concentrate on building medical electronic devices, electronic circuits, and telecommunication systems. You see some of the pictures of the work we have done. Blindness is a very serious perceptual disability which is depriving a human of up to 90% perceptual abilities. Of course, the consequences are exclusion from social and professional life. Such a person is dependent on others, and the costs of supporting this disability are really large. The history of building assistive devices goes back to 19th century, in which we have a Polish contribution by Kazimierz Nowiszewski, an ophthalmologist who worked in Vilnius, in Warsaw, and he built a special device called artificial eye, in which he applied selenium cells and converted them to acoustic signals. On the picture, you see another prototype built in Pomeranian University of Technology much later. It is a device, as you can see, quite large and cumbersome and has not found any practical acceptance of the blind community. If we are talking about building assistive devices, of course, we are looking for means to substitute vision by other senses, for example, hearing or touch. We should be aware, however, that lower information capacity can be offered by these communication channels, much lower than the visual system can offer. If we are undertaking the problem of presenting the environment, of course, there is a question how to present objects by using, for example, sounds. One problem is presentation of the azimuth, another is the problem of the distance of objects. Azimuths can be presented by using special head-related transfer functions. These are the functions which simulate different filtering capabilities of our ear to perceive direction of the sounds, and this is what we have used in our experiments. And also distance is usually coded by more than one parameter, for example, amplitude and pitch. Object geometry can be commented by verbal comments. Here we see an example of a system which is called the voice. As you can see, it is a very complex method of presenting the environment and required 6 months of training. It is interesting that to know that if no signals reach the visual cortex, we can find a sort of round loop to reach the visual cortex by stimulating our touch or auditory senses. And by this means, the visual cortex can be stimulated and a blind person can build a cognitive map of a space. This has been proved by experiments in using fMRI scans, whereby we can see that by activating auditory cortex related to space perception, after 2 months or 2 weeks, of training, activation of visual cortex occurs, and this helps blind persons to have space perception by means of acoustic signals. In our early experiments, we have used different methods to sonify the environment. This is the work Pearse from left to right. You can see we are using to demonstrate distance of Our work dates back almost 20 years ago. We have started the first project, and we had 2 other research works, and finally we also participated in the European project Horizon, in which we were a technical partner, and I will show you some results of the work we have been proposing to the consortium. Here is the concept of our early work, in which we used stereo vision to present depth of the environment, in which, as you can see in this picture, the distance to objects in the space are coded by different colors. The hotter the colors, the closer the object. Then we attach different sound icons to the objects and present it to the blind person. Special technology which we have been using is head-related transfer functions, in which we define the acoustic properties of our hearing systems, and by using these simulated filters identified by this measurement system, we can achieve this space perception simulating the 3D environment, acoustic environment. Here is the presentation of this technology we have used to present the environment. It's one of the person to different cases, 100% mobile. But it's quite a different way to present the environment. As you can see, person can maneuver within this environment. Here is the summary of the work we have done in our sound of vision system, but probably better way to present this is to show our contribution to the project, in which we have built a system which is presenting the obstacles in the environment by using, as you can see on the left and right hand side, vertical yellow sticks showing objects which the blind person should avoid. As you can see at the bottom, we have a mesh, hexagonal mesh, showing a safe space in which the blind person can move around. So we will see, this is the campus of our university, and you can see that this technology, which is using special algorithms called particle filters, can run this program in real time and present the obstacles. Our recent work also has concentrated on testing how different sounds are effective in echolocation. We have run trials with 12 blind persons and 40 sighted persons. And in general, the results show that blind persons shown here in these darker bars, vertical bars, are a bit better in echolocating. And interesting conclusion was that the best sounds we can use for echolocations are the sounds which have the main energy located in the bandwidth between 3 and 4 kilohertz and have wide spectral content. Here we have a view of a different system across the years. As you can see, the latest one is fully mobile. Of course, we have some cables, but this is quite portable, and we carry on experiments with this system. Some recent results using this system are presented in this video.
1.5, empty.
On top, you can see the top view,
1.4,
in which green color is showing the
0.9,
safe space.
0.7.
Here, this color map is showing the depth of the environment, in which hot colors show very close objects.
2.6, empty.
The closer we are to the object, the
1.7.
color becomes warmer. As you can see. Also, we hear some comment informing the blind person about the environment. These comments
1.7.
become faster and faster when the person is approaching cloud.
1.1, 0.9.
You will hear it in a second.
2.6, 2.2, 2.3, 2.4, 2.5, 2.6, empty, empty.
This is distance.
2.5,
meters.
2.3, 1.6, 1.7, 2.0, 2.1, 2.2, 2.0.
We see this angle here, the corner.
1.8, 0.5.
And the person is touching the wall. Of course, assistive technologies go much further, and there are attempts to build visual prostheses. This is the research, very ambitious, but not all persons can be accepted by the surgeons in such operations, but first operations have been already done, definitely. This is a high hope in this line of research. As a concluding remark, I would like to underline that quite frequently we are really thinking of how this modern technology can be adapted to blind user, but really we should approach the problem from a different side, as commented by Smith Catwell Eye Research Institute. So we should rather ask what information is really needed by a visual persons and how it should be presented so that it would be the most helpful for the blind person. And then we should look for the proper technology to solve the problem. So the user-centered design is the key to success. I would like to capture your interest with my book I have wrote a few years ago on the systems we have been building at the Lodz University of Technology. And finally, I would like to express my gratitude to different institutions who have been helping us in these projects. First of all, to Polish Blind Union, in which we have found much help in cooperating with blind person and running the trials, and of course other institutions who have been funding our research, which is costly and very ambitious. And this is not the end, I hope, and will bring help to blind persons. Thank you very much for the attention.
I'd like to thank the organizers of the Artificial Intelligence in Ophthalmology 2023 conference for giving me this opportunity. My topic is Explainable Artificial Intelligence for Diabetic Retinopathy. I'm an ophthalmologist and I head the Teleophthalmology department in Shankar Nethralaya Eye Hospital, Chennai. Financial disclosure nil. I do not have any affiliation, financial or otherwise, with a commercial organization that may have a direct or indirect connection to the content of my presentation. Worldwide, diabetics in the age group of 20 to 79 are 563 million. By 2045, we expect the rise to be 783 million. In India, the age group of 20 to 79 years, it is 7 million. 1 in 6 adults with diabetes in the world come from India. Epidemiological studies have shown that 1 in 3 persons with diabetes have diabetic retinopathy and 1 in 10 have sight-threatening diabetic retinopathy. Diabetic retinopathy classification is based on the International Classification of Diabetic Retinopathy Severity Scale. Non-proliferative diabetic retinopathy and proliferative diabetic retinopathy. Now, non-proliferative is mild, moderate and severe diabetic macular edema with center involvement and not central involvement, and then proliferative diabetic retinopathy. Artificial intelligence screening and prediction models. The advantages of artificial intelligence are, from the back of the eye to the front, artificial intelligence is expected to give ophthalmologists new automated tools for diagnosing and treating ocular disease. The sensitivity and specificity of artificial intelligence models when compared to expert opinion was 90.5% and 93.3% was the specificity. Disadvantage of artificial intelligence are the development concerns, ethical, clinical implementation concerns, lack of standardization, and clear legal liabilities. The limitations in artificial intelligence can only be as smart or effective as the quality of data you provide. Algorithmic bias is there, and it's a black box nature because we are not clear how it arrives at the diagnosis. Artificial intelligence for diabetic patients to identify and eliminate 67 to 82% of diabetic patients with no DR by screening by paramedical staff using artificial intelligence, to identify 18 to 33% of diabetic patients with DR using artificial intelligence, and follow referral to the ophthalmologist for further investigations and treatment. decrease the incidence of newfound adult blindness in diabetic patients. So it is very important in diabetic patients to identify those with diabetic retinopathy, and the 18 to 33% of diabetic patients with DR should be identified, and there definitely should be a referral. Now, the 2020 American Telemedicine Association guidelines for DR screening using artificial intelligence are: Category 1 identifies patients with presence or absence of DR. Category 2 identifies patients with or without sight-threatening diabetic retinopathy. Category 3 identifies non-proliferative diabetic retinopathy, mild, moderate or severe, and proliferative diabetic retinopathy, and macular edema, with sufficient accuracy for appropriate decision making. So all the stages of diabetic retinopathy, both non-proliferative diabetic retinopathy as well as proliferative and macular edema, identified in category 3. In category 4, that equals or exceeds the ability of ETDRS photographs, which are the gold standard, to identify DR lesions. To determine levels of DR and macular edema, Category 4 validation indicates that the program can replace ETDRS. Now, if you see fundus camera transition, initially throughout the century it has been tabletop fundus cameras. Now you see ultra-wide field fundus cameras as well as smartphone-based ophthalmoscopes. Non-mydriatic retinal imaging, a single field is enough as a screening tool. There is level 1 evidence that single field fundus photography with interpretation by trained readers, artificial intelligence, can serve as a screening tool, but it's not a substitute for a comprehensive ophthalmic examination. Now, ETDRS, the 7 fields, are the gold standard for diabetic retinopathy. They require dilatation as well as a trained person to do the photography. The next one is ultra-wide field imaging, which is a newer technique, and you can see fundus up to 200 degrees. This can be non-mydriatic or mydriatic. In DR screening, it's important to address the illumination and contrast of fundus photos. Difference in brightness and contrast increase the complexity of the background. The AA should be familiar with variations in the retinal photographs. Now, the DR screening system in the outpatient department, when diabetics come, they look for the lesions of non-proliferative diabetic retinopathy, like microaneurysm, small hemorrhages, hard exudates. When it's severe diabetic retinopathy, you will see diabetic macular edema as well as soft exudates. In proliferative diabetic retinopathy, you'll see vitreous hemorrhage as well as neovascularization and tractional retinal detachment. Deep learning is a convoluted neural network, and it's a black box phenomenon. Basically, we don't know how the diagnosis is made in such conditions. In India, the Google DL system, the deep learning system, achieved a sensitivity and specificity of 89% and 92% respectively on data from the Aravind Eye Care Hospital, and 92 to 95% respectively on data from Shankar Nethralaya. The deep learning system's performance was superior or comparable to that of ophthalmologist reference standard. If you see the various systems developed by various people for artificial intelligence, in 2016, based on the color fundus photographs, the disease diabetic retinopathy was identified, whether presence of disease or absence of disease, referable diabetic retinopathy, as well as vision-threatening diabetic retinopathy and macular edema were identified, with a sensitivity of 96% and specificity of 87%. Gulshan et al., the Google, was identified in 2016 with color fundus photographs. Here also the presence or absence of diabetic retinopathy and the various stages of diabetic retinopathy and stages of sight-threatening diabetic retinopathy were identified. This had a sensitivity of 97% and specificity of 93%. Ting et al. In 2017, again based on color fundus photographs, were able to identify diabetic retinopathy as well as glaucoma as well as age-related macular degeneration with 90% sensitivity and 91% specificity. Again, Amraf et al. In 2018, based on optical coherence tomography, identified diabetic retinopathy and diabetic macular edema, the sensitivity of 87% and specificity of 90%. Lee et al. In 2021, again based on color fundus photograph, was able to identify diabetic retinopathy, various stages, as well as diabetic macular edema, the sensitivity of 92% and specificity of 96%. Hribar et al. In 2021, based on color fundus photographs, was able to identify the presence or absence as well as the various stages. Sensitivity was only 74%. Specificity was high, 93 to 97%. Liu et al. In 2021, using optical coherence tomography angiography, determining the retinal vasculature, was able to identify the presence or absence of diabetic retinopathy. The sensitivity of 86 to 97% and specificity 94 to 99%. If you see the screening strategies of diabetic patients conducting diabetic retinopathy camps, you can do it in several rural areas conducting camps. You can do household enumeration of diabetics. Diabetics can be examined in the diabetic clinics and general hospitals, or we can also do it with the help of physicians and local NGOs. What is required is engagement with physicians, ophthalmologists, endocrinologists in screening diabetic patients, as most activities should entail joint planning, implementation, and monitoring. Now, presence of the diabetic retinopathy, artificial intelligence tool in the field, the false negatives, that is, the missing patients with the disease, should be minimal. There must be a specific report indicating the severity scale of diabetic retinopathy for all false negatives. And it should be important that sight-threatening diabetic retinopathy should not be missed. The limited amounts of false positive, that's false alarms, are acceptable as there's an increase in referrals to the hospital. The image artifacts, dust particles, and other disruptions like hyper and hypopigmentation, drusen, affect the performance of diabetic retinopathy system by reducing the specificity. International conscious that DR screening programs must ensure 80% sensitivity and 95% specificity with 5% technical failure rates. Now, artificial diagnosis identifying proliferative diabetic retinopathy is very important and essential. Here you can see the fundus photographs with new vessels on the disc, as well as retrohyaloid hemorrhage, glial proliferation. So these cases require urgent referral and treatment of the proliferative diabetic retinopathy to prevent visual loss in the patients in the productive years of life. Here, diabetic macular edema is also a part of sight-threatening diabetic retinopathy, and you have the surrogate markers, which are hard exudates and the succinates. In the left eye, you can see the accumulation of fluid, macular edema. Now, diabetic macular edema, 1/3 of DR patients have diabetic macular edema, and 1 in 16 DR patients have clinically significant macular edema. The diabetic macular edema disrupts the retinal symmetry and is particularly triggered by vascular endothelial growth factors, VEGF. Optical coherence tomography measures the retinal thickness that is caused by the presence of diabetic macular edema. Intravitreal injections of anti-VEGF have been the most practiced treatment. Artificial intelligence prediction of diabetic macular edema treatment. DMA is treated with anti-VEGF injections to improve and stabilize the quality of vision and ultimately to improve the quality of life, which is severely threatened by visual loss. Interacting clinical factors such as duration of diabetes, glucose levels, glycosylated hemoglobin, previous treatments taken, number of anti-VEGF injections, and the underlying ophthalmic conditions which can influence the response towards the treatment of diabetic macular edema. AI can predict patients' response to anti-VEGF treatments. AI tool improves the efficiency of DME disease management, providing the best line of treatment to patients, resulting in cost savings to the patient. 2020 American Telemedicine Association Guidelines for Diabetic Retinopathy, AIs, autonomous AI in healthcare makes clinical decisions without human oversight. Patient outcomes, reference standards, accountability for medical liability are primary concerns. Level of evidence is required for diagnostic accuracy and system design. Also for transparency and adaptability of the system. DRAI that operates as a medical device and follows the International Medical Device Regulation Forum guidelines. Now, automated computerized screening system further reduce the workload for human graders. Additionally, the process is considerably cost-effective in rural areas and in less developed countries compared to manual grading. Automated diabetic retinopathy screening reduces the cost for repetitive screening. So it's very important to incorporation of the artificial intelligence for routine screening of diabetic patients, which will enable wider deployment and empower minimally skilled technicians to participate in eye care delivery process. Ethics in healthcare for artificial intelligence are: patient must give informed consent that patient is willing to diagnose with the help of artificial intelligence. Liability: AI-aided DR diagnosis, fully automated AI system, digital diagnose assumes liability for the performance of the AI. Build metrics around safety, equity, efficiency, transparency, and accountability for the artificial intelligence. Now, artificial intelligence bias should exclude racial and ethnic bias. And it's also important the artificial algorithm design, including the use of biomarkers, should be there instead of the prior, less blank state black box algorithms, the distribution of the training set. IDX-DR is a biomarker-based artificial intelligence system, and it's not a black box system involving the latter's many risks. So the legal questions have to be answered. How can AM system ensure patient consent? The patient should be well aware that artificial intelligence is making the diagnosis instead of the doctor in place. How will questions of liability be addressed? Is the system or the software which diagnoses is liable? That has to be taken in. How does DRAA fit in the existing ethical frameworks in India? For undergoing diagnosis by artificial intelligence, will the insurance make the payments? And who's accountable for the errors, if errors occur? How can the security and accuracy of AI solutions be ensured in the health sector, as individual lives can be at stake and highly sensitive data is being handled? So when you want to, in future, scale up artificial intelligence detection of diabetic retinopathy, for all artificial intelligence enabled retinal image analysis to be practiced, there's a need to consider government regulatory norms, licensure, and cost. Diabetic retinopathy, artificial intelligence operates as a medical device and follows the International Medical Device Guidelines. Joint planning, implementation, and monitoring of diabetes screening by ophthalmologists, physicians, and endocrinologists. We need medical practitioners and engineers to collaborate and work towards developing and improving new technologies for diabetic retinopathy, artificial intelligence that will aid in disease identification, prognosis, and monitoring of treatment. We do need to have further work on adopting standard guidelines for adopting artificial intelligence retinal analysis for DR screening programs. As a summary, incorporation of artificial intelligence for routine screening of diabetic retinopathy, the clinical flow, large population studies at a national scale will enable wider deployment, empower minimally skilled technicians to participate in the eye care delivery process. This is a presentation from Shankar Nethralaya. I once again thank the organizers for giving me this. Thank you.
Hello everyone, my name is Jing Kai from Eye Center of the Second Affiliated Hospital of Zhejiang University. Today my topic is Artificial Intelligence Aided FFA Images Interpretation and Clinical Evaluation. Here is the contents of my presentation. First, AI-aided diagnosis and treatment of eye disease. Second, AI-assisted FFA report interpretation. Third part is the clinical application of our AI system. We declare no financial disclosure. First, AI-aided diagnosis and treatment of eye disease. Retinal disease are important cause of blindness. According to epidemiology statistics, retinal disease can lead to decreased vision and are the primary cause of blindness. Diabetic retinopathy, age-related macular degeneration, and glaucoma are the three most common diseases with high rates of blindness. Here are the current status of eye disease screening in China, the current situation of medical and health services, large population base, uneven distribution of medical resources, and large differences in regional medical level. Ophthalmic medical resources are scarce. At present, there are only more than 40,000 ophthalmologists in China, equivalent to 46,000 Chinese people who can be treated by one ophthalmologist. The manual diagnosis is insufficient and subjective. It takes nearly 1 minute for an ophthalmologist to interpret an image, while AI can process 10 images in 1 second. AI screening for diabetic retinopathy is a research hotspot. However, the current application of AI in diabetic retinopathy assisted diagnosis mainly focused on the fundus screening, and there are few studies on automatic recognition and quantitative analysis of lesions. AI is still unable to meet the needs of DR clinical diagnosis and treatment. FFA is an important clinical examination in the diagnosis of retinal diseases such as DR. It can accurately display the structure of fundus blood vessel and is the golden standard of the diagnosis of fundus vascular diseases. However, the interpretation of FFA report is time-consuming and laborious, and there's few relevant AI research. Here are the challenges in interpreting AI-assisted FFA reports. Clinical needs are FFA reports require experienced ophthalmologists to interpret. The clinical diagnosis level is uneven, time-consuming, and labor-intensive. Lack of relevant AI research. Advantages of AI is the systematically processing reports, faster speed, and low cost. Deep learning systems have stable performance, improve diagnostic skills, and promote medical homogeneous generation. Here are the characters of FFA. Large amount of information, including various information such as eye type, face, location, lesion, etc. Time information needs to combine pre and post temporary information to distinguish lesions. Reading FFA takes time, requires specialized knowledge and clinical experience in retinal diseases, making report analysis more complex. Here are our AI research platform. We have clinical platform, engineering platform, and translation platform. The Jeoung University Eye Hospital have annual patient of 900,000 and annual surgery 100,000. We have multi-clinical center collaboration and large clinical data. And also we have intelligent healthcare and deep learning disciplinary platforms and international cooperation platform. The second part is AI-assisted FFA report interpretation. First is the lesion classification. We constructed a deep learning system-based lesion multi-label classification system to help doctors interpret FFA images, automatically identify non-perforation errors, microaneurysms, linkages, and laser scars. And the AUC under the curve is 0.87 and 0.96. We constructed a non-perfusion errors automatic analysis system based on deep learning, performing automatic segmentation and recognition of the lesions, assisted in the design of fundus laser passes, and automatically recognize AUC up to 0.97. We establish image intelligent analysis technology based on temporary neural networks, dynamic identification of linkage points, achieve precise recognition of later targets, and effectively eliminate false positives, highlighted by journals as breakthrough in artificial intelligence for ophthalmology. Then the DR gradient diagnosis, we established a DR gradient diagnosis system based on deep learning and achieved the gradient diagnosis accuracy of 96.17%. And finally, we established a deep learning system to interpret multitask AI system of FFA images. The FFA image was obtained from 845 patients, 1,558 eyes, and 50,599 images. We established a multitask AI system that can automatically interpret FFA image quality, fundus position, face, eye type, and fundus lesions by deep learning system. The accuracy is 63 to 88%. And the human machine comparison shows the accuracy of AI system is comparable to that primary ophthalmologist. False positive and false negative analysis have identified the direction of future improvement. The third part is the clinical application of our AI system. Here is the software and the copyright of our AI system. The AI system has been promoted and applied to 9 medical institutions nationwide, with a total of 18,000 cases, including the Peking University Third Hospital, Tianjin Medical University Ophthalmology Hospital, and Shandong Provincial Ophthalmology Hospital, and etc. Here is our software in our hospital. And we can analyze the color fundus images and also the FFA images with show the different lesion classification and the diagnosis of the AI systems. Here's different patients and different interpretation of the reports. Here's our publications. An AI-assisted FFA report interpretation system was established to assist diabetic retinopathy and other retinal diseases detection and classification, and accurately improve the comprehensively diagnostic ability of the retinal diseases. We published 5 relevant peer-reviewed papers and authorized 1 patent and 1 software copyright. Thank you for listening. Bye-bye.
Hello, my name is Haoyu Chen from Joint Shantou International Eye Center, Shantou University and the Chinese University of Hong Kong. It is my great honor to participate in this important symposium, and today my topic is uncertainty-inspired open-set learning for retinal abnormality identification. I have no financial interest to disclose. As we know, screening of retinal diseases is very important because there is high prevalence of retinal diseases, and retinal diseases can cause irreversible blindness, and also the diagnosis of retinal diseases require expertise. Therefore, screening based on fundus photo is a good solution for these scenarios. Traditionally, screening used trained human data, and it has been proved very successfully in reducing blindness caused by diabetic retinopathy. However, the human data require many manpower, and therefore, how to reduce this manpower and improve the efficiency of screening is important. Recently, the development of artificial intelligence, especially deep learning, has been successfully applied in the field of image classification, and it has been proved that deep learning can successfully classify the fundus photos of diabetic retinopathy, glaucoma, age-related macular degeneration, and even multiple retinal diseases. However, there is still barrier of the implementation of the AI model in the real world. The open set environment is a major problem. So usually the AI model is trained in a closed set environment. So we have many preset criteria. For example, we only use several common diseases to train the AI model, and we also use this common retinal disease to test the model, and we only use high quality image and have enough sample size. However, in real world, there may be some rare retinal disease, so which is out of the category of the trending models, trending diseases, and also the patient may have untypical presentation, and also we may have some image with low quality, and also there may be some other type of the image we used to test the AI model. So to solve this problem, so we propose an uncertainty-inspired open-set learning model. So this is the flowchart of this study. So we trained the traditional AI model and also our UIOS model with 9 categories of retinal diseases. And then we test this model with fundus image within this 9 category. Then the traditional AI model will output a probability of this 9 category, and then we can make diagnosis. If we test this AI model with fundus photo outside this 9 category, then the traditional AI model will still output a probability of this 9 category, which may lead to a misdiagnosis. Well, our AI model, our UIOS AI model, when it is tested with an image within this 9 category, it will output a probability of this 9 category and also an uncertainty score which is lower than the threshold, which suggests that this diagnosis have high confidence. And if we test this our UIOS model with image outside this 9 category, then it will output a very high uncertainty score. Then it suggests that this result is unreliable and it requires a human grader to track this image again. So this is our method. We use 3 common retinal diseases data set which have a 9 category, and we have the first one with typical presentation, and the second one with ambiguous features, and the third one is an independent data set. And we also have 2 rare retinal diseases data set which is outside of this 9 category, and they are independently. And we also use 3 non-fundus data set which include natural image and also 2D OCT image and also some OCTA images. And this is the sample size of the these 3 data sets, and we separated this typical common retinal disease data set into the training set and validation set and also the testing set, while these 2 data set is used for the testing only. And this is the criteria of the typical and the non-typical presentation of these 9 diseases. And this is the diagnosis of a number of images in the rare retinal diseases data set. These 2 rare retinal diseases data set. So this is the methods of our AI model. We used a pre-trained ResNet 50 for the traditional AI model, and then we calculate the evidential uncertainty scores based on this ResNet 50. And this is the formula of the uncertainty score calculation. And I will skip this part. And if you have interest, you can read our paper. We deposit in the pre-printed data set. And this is the formula to calculate the loss function. And also we automatically determine the uncertainty score, the threshold of uncertainty score. So if it is higher than this threshold, so then we consider the result is unreliable. And if it's lower than that, and then the result is reliable. So this is the result of the F1 score. So we can see that our UIOS model have better performance compared to the standard AI model, and also it get further improvement with the strength holding strategy. So you can see that the F1 score reach more than 99 in the internal testing dataset and 97 in the and 91 in the two independent dataset. And this is the result of precision, sensitivity, and specificity. And this is the confusion matrix. So we can see that compared to the standard AI model, the image of misdiagnosis is significantly reduced. And this is the ROC, the receiver operating curve. So we can see that compared to the standard AI model, so our UIOS model have better performance. So you can see the AUC get improvement, and also with this strategy, the strength holding strategy, the result get further improvement. So we can see that it can get very good result in the internal testing set, and even for an independent testing set, the performance is also very good. And for this untypical data set, so we can see that it can also be very good improvement compared to the standard AI model. And so this is the result of the distribution of uncertainty scores in different models. We can see that the result in the validation set is very good. So we can see that it has a very low proportion of the image higher than the threshold. And in the performance in the internal testing set is also very good. And also for this independent testing set, and also the untypical data set. But for this rare retinal disease data set, and all these two rare retinal disease data set and some other data set, then the most image are higher than the threshold. So this is some example of the testing. So we can see that if we use these two typical presentation of the common retinal diseases, then we can see that both the traditional AI model and our AI model have good performance, and our AI model can also output a low uncertainty score, which suggests that this diagnosis is reliable. And for the untypical presentation, then our result can the traditional AI model may output a wrong diagnosis, but our model can output a high uncertainty score, which suggests that the result is unreliable and require a human grader to double check. And this is the rare retinal diseases, and so we can see that our AI model output a high uncertainty score, and also for the OCT image and OCTA image and the natural image, our AI model also output a high uncertainty score, which suggests that the requirement of a human grader. So there are several methods to calculate the uncertainty. So most of the literature use this Bayesian neural network, which draw out some component of the network and then calculate different result, and then calculate the variation of the result as the uncertainty. And there are also some article use these ensemble measures. They use different network and then get a different result, and then also calculate the variation. And the third one is the test time data argumentation. So they use different methods to argument the image and then calculate the variation. Our study use this deterministic network, so we can directly calculate the uncertainty score based on this network without further need of the other experiments. And there are already some articles to reported to detect abnormality in fundus photo. However, they are only trained with normal image and to detect abnormal image. They cannot detect the out of category image based on multiple classes classification. And there are also some reports of uncertainty in medical image classification, but mostly they are based on the Bayesian uncertainty, and they are usually used for the image segmentation. And there are also some binary classification and also multiple classification, but they are not for the detection of the out of category abnormality. And this study is the first one to apply this uncertainty strategy in this multiple classification and to detect out of category images. So our strategy mimics the young ophthalmology learning. So in young doctor was trained with common retinal diseases, and when they see patients with the diseases they have learned, they can diagnose the patient with confidence. But if they see the patient with disease they have not learned before, then they will seek the help from the senior doctors. And our AI model, our UIOS model, meets this process of the young doctor learning. The contribution of this study is that we developed new algorithm, including new loss function and new strength holding strategy. And we also have new clinical application. We apply it in multiple retinal disease classification, and we detect out of category image and out of distribution images. In future, we will train more category, and we will retract the image with high uncertainty score, and we also will apply it into other modality of medical image. In conclusion, our UIOS model combined with stress holding strategy can accurately classify 9 common retinal diseases and also detect rare retinal diseases and other out of distribution samples, and we can avoid misdiagnosis of retinal diseases and also provide a robust measure to screen retinal diseases in the real world. I would like to thank my collaborator, Dr. Fu and Dr. Wang, Dr. Chen, and also my students and also my colleagues. Thank you very much.
Thank you, all the speakers. So good to have you with us to the discussion part. And of course, we are open for questions from the audience. I remind that you can put the questions on the chat. And in the meantime, we can start the discussion between us. And well, I have a question to Professor Chen. Have you thought about making your algorithm open access to enable other researchers to work on that, to test, to maybe also to make it better? I mean, something like that.
Yeah, thank you very much, Professor Yaski. So yes, so actually we have already submit this paper to open to a preprint deposit service, and we also opened the code. And currently, the manuscript is under review in the Journal of Nature Communication. And once it is accepted, so we will make it open access, and so it can
have everyone can test the algorithm, and we'll also help us to improve our algorithm. Thank you.
It's very good. I mean, it's quite rare, and really, I must congratulate for doing that. I mean, because of course, one of the problems for many of us is that the algorithms are not made available for other researchers. That's why we cannot really verify the everything. I mean, credibility, reliability. So when your paper is published, let us know. We'd be happy to work on that with you. I mean, and to show maybe some who knows, I mean, improvements or some additional aspects. So I have a question. We still have no questions from the audience to Dr. Jeoung. I mean, obviously you have a lot of experience in Diabetic screening based on AI. What could you tell us about the registration in India? Do you have any particular way of AI-based devices registration? Like, for example, we know that in Europe we have CE mark, and you know, in US and China FDA approval. So, do you have any AI-based devices in India?
Actually, if you see in India, many people are trying to make artificial intelligence devices, but Google is one person who has come into Aravind Eye Hospital and Shankar Nethralaya itself. They've done the deep learning algorithm where it can be used for many people. So basically, that algorithm of Google's, which has been tested out, has a very good sensitivity and specificity, and it's being used in the rural camps. So we can use it, and it sensitivity and specificity is over 90%. And basically, if you see the number of ophthalmologists are very less in India, and the number of diabetics are more. And day by day, the number are increasing. So the artificial intelligence tool created by Google is very useful. Are you able to hear me?
I must tell that I have some difficulties because I cannot hear. I cannot hear quite clearly, but I'm not sure if it's on my side or your side. So, well, could you summarize how many AI-based devices you have registered in India for ophthalmology, of course?
How many AI-based devices?
Yeah, registered in India.
Yeah, that is what in India, the government has gotten guidelines for AI, but independent diagnosis by AI is not allowed. It has to be supplemented by a doctor. And the number of AI devices, Google has done a lot of work in India.
So your experience, I understand. So your experience, as I understand, is based mostly on the Google AI.
Google, yeah, Google. Yeah. They worked in a hospital.
I have a well. You mentioned, as a matter of fact, it is quite interesting in your presentation that it is that one field image is enough for diabetic retinopathy screening. What kind of evidence do we have for that? That just one field image is enough?
Yeah, what we do is we conduct teleophthalmology camps, about 20 camps in a month. So our rural patients, we take non-mediatic images at the campsite. And then the algorithm is run over the retinal images. We have a large database of retinal images from the camps as well as from our hospital. So we have tested it on it. Are you able to hear me?
Yes, but not very clearly.
Not very clearly, every second word. So we must make the whole, let's say, understanding based on just not the full sentence, yeah. But yeah, and well, we are at the end of the discussion time. So let me thank you so much for contributing to our conference and being with us for the discussion part. Thank you so much.
Thank you. Thank you very much.
Dear colleagues, I would like to start the session number 4. What do ophthalmologists expect from AI? And the introductory lecture to this session, because we will have the panel discussion after the lecture, is Professor Leo Schmetterer from both Europe and Singapore, because his list of affiliations is pretty long. It's a Singapore Eye Research Institute, and this is a Center for Medical Physics and Biomedical Engineering, Medical University Vienna, but also Institute of Molecular and Clinical Ophthalmology in Basel. And he will speak on limitations of AI application to ophthalmology and how to overcome them. Then we will have the panel discussion, and we will have Mr. Georgi Shakirin, who is the head of AI at Carl Zeiss Meditech. And we will have with us Professor David Peleas, who is the professor and the head of the Department of Ophthalmology at Maimonides University of Buenos Aires. And he is one of the leading people in AI in South America or Latin America. So let's start with the first lecture, please.
Hello everyone. My topic today is limitations of AI application to ophthalmology and how to overcome them. I have no financial disclosure related to the topic of my talk. Now, if you look into Medline, and this I did yesterday, then you can see that the number of publications related to deep learning in ophthalmology is increasing every year. And I think for a number of years we will see a continuation in this trend. And it's particularly in the last 5 years that really a lot of papers have been published. But if you look into the implementation, there is a slightly different picture, and I would like to present to you a systematic review that was now published 10 years ago on the implementation of patient decision support interventions into routine clinical practice. And the conclusion that was drawn in this paper is it seems too early to make firm recommendations about how best to implement patient decision support into routine practice, because approaches that use a referral model consistently report difficulties. And it is now 10 years later that we are still faced with these problems, and whereas from a research perspective many solutions have been published and have been proposed, very few are actually used in practice. Now let's go a little bit more into the details of this. As you know, what is usually required is that you split your data set into a training data set to train the models, into a validation set to make sure the models are not overfitting, and into a test dating set to determine the accuracy of the models. Now, a lot has been discussed about the number of data that is required, and obviously this is an issue, and you need a lot of data to train a good CNN. But there is other issues as well, and one of the key issues relates to the stage of the disease. And this is, for instance, in a study where you can see that this is a study in primary open-angle glaucoma, that very few early glaucomas were included. And even if you have in total a large number of glaucoma patients in a CNN, but a certain stage is underrepresented, you cannot assume that the CNN works well for early glaucoma. The CNN may work well for stages 2 to 4 in this case, but definitely not for stage 1. And this is not only true for open-angle glaucoma, this is true for all types of ocular diseases. For instance, it's a challenge also in diabetic retinopathy. If you have, for instance, very few cases of proliferative diabetic retinopathy, the CNN is not going to perform very well. Another issue relates to the ground truth as reference standard. Usually this is clinical assessment of a disease, but as you know, this can be quite complex in some cases. For instance, in glaucoma, we have good clinical assessment for late-stage glaucomas, but in early-stage glaucoma, this is much more tricky, and there might be a clinical over- or underdiagnosis of glaucoma. And we need to understand that the CNN cone can only work as well as this gold standard. And if there is a lot of misclassified subjects in the gold standard, then of course the CNN cannot correct for this and will also fail. Now, an additional challenge comes from the black box approach. Of course, there is nowadays opportunities to look into heat maps and see which parts of an image are taken to make a decision. And you can see here that of course, in the case of glaucoma, this is largely restricted to the optic nerve. But you can also see that if this fails, if the CNN may take totally different regions of the image to classify this as glaucoma or not, and then the system will most likely also fail. Now, I'm not going to talk very much about the clinical assessment of diagnostic performance. I would just like to mention that the FDA has recently released a document about a regulatory framework for modifications to artificial intelligence and machine learning based softwares as a medical device, and this is more or less now also used by the EMA, and it is currently the basis for approval by the competent authorities. But there are many challenges in implementation. The one is the science of deep learning. We have many deep learning solutions that were never tested in a real clinical applicability, but they stem from randomized trials or from population-based studies, but not truly from a clinical setting. And this has the challenge that you can have a shift in data, that you can have fitting of confounders, that you have an unintended discriminatory bias, and it may be difficult to generalize this to new populations, particularly if these populations are of different ethnicity. Then we have logistical difficulties in implementations. Are the technical requirements available? And actually in many settings and many hospitals, these IT requirements are not in place, and it is quite financially demanding to set up such a system. And how does the DL system fit into the workflow, and how does it impact the cost effectiveness? And this is a complex one, because at the end of the day, the nurses, the administrators, the doctors, they all need to find a way how to optimally implement this, and at the end of the day, we also need to evaluate whether this really comes with any cost savings. And then there is, of course, the social cultural changes and the patient's perception. So, to which degree will the deep learning workflow be accepted by the healthcare providers, and how will the patients accept it? And it is also a question, how shall we inform the patients about this, that a deep learning system has taken part of the decisions? Is this part of the informed consent that we provide? And how will the patients perceive it? It might well be that the patients will understand the mistake that is made by a doctor or a healthcare professional, but they will much less understand the mistake that is done by a machine. Another real-world challenge is particularly true when you use fundus photographs, and this relates to the number of non-gradable images. And of course, this depends on the fundus camera that it is used and whether this is a standalone or a handheld system. Usually you get better results with a standalone system, but independently you need training and quality control on site. And this is a big problem, because this is again quite money expensive, and if you need train regularly, if you have quality control of the images, if you have the standard operating procedures in place, this is a lot of effort and requires manpower. I would also like to mention that this depends to a large degree on the study population, for instance, the degree of cataracts. And this is particularly a problem in low-income countries, where I've also seen that sometimes fundus photographs that are collected are of very poor quality, simply because the patients have a high degree of untreated cataracts. And finally, there is a challenge with the costs and burdens associated with false positives and false negatives. And again, this depends very much on the geographical framework and the socio and economic conditions, and also in the insurance system and in the healthcare systems. But what is true, particularly in low-income countries, if somebody is false positive and is referred to a doctor, this usually means that the patient has to pay for travel to see an ophthalmologist, and the patient also has to take a non-pay leave from work. And this is a significant financial burden, and if then the result is false positive and there is actually no need to have an ophthalmological appointment, this is a burden to the society. Of course, we can run CNNs at sensitivities that provide very few false positives, but then we have a lot of false negatives on the other hand. And this is something that I think we still need to figure out, depending on the clinical setting, what is the good way to run such CNNs. And there may not be a common solution for all healthcare systems and all problems, but this really needs to be customized together with all the stakeholders. Finally, I would like to mention that we need to define what we shall use AI for. And let's take the example of glaucoma here. Shall we use it for diagnosis? Shall we use it for screening? Or shall we use it for follow-up and progression analysis? Honestly, I think that there is not a good case for using it for diagnosis, because the diagnosis will at the end of the day be always done by a clinician. So the question is, can we do screening with it? Now, for screening you need a very high AUC, and you can see that the AUC for detecting glaucoma based on OCT is largely dependent on the stage of the disease. We do very well in the late stage diseases, but then it's anyway obvious how to diagnose this. But actually OCT doesn't do so well in the early stages. And the question is, can we improve this with AI? Now, let's look, does glaucoma in principle fit into a study, into a disease that can be selected for screening? And most of the criteria are fulfilled. It is a significant burden. It has a detectable stage. We understand the natural history. Early detection has an outcome benefit because we can treat the patients and because effective treatment is available. But the real question is are there appropriate tests available? And this is linked to the question, do we have facilities for screening? And only if these two things are fulfilled, there will be political willingness to support such a program. So obviously the appropriateness of the test and the political willingness is currently missing. And if we want to use this for screening, we need to come up with very robust CNNs that provide extremely high sensitivity and specificity. So in principle, glaucoma could be a disease that is to be selected for screening, but it is a challenge in terms of appropriateness of the test and cost effectiveness, and to convince the politicians that we should do so. So the practical hurdles for implementing AI are related to reimbursement, and accordingly inclusion of AI will change the distribution of money within the healthcare system. I do not believe that there will be less ophthalmologists required, but I do believe that the salary of ophthalmologists will go down with AI. Then there is a question of liability. To which degree will the makers assume? And should we run AI systems at very high sensitivity? This will result in very many false positives in order to prevent that we miss subjects, but maybe we then need human overreading to increase the specificity. And with this, I would like to thank you for your attention.
Now we have time for a discussion. I would like to welcome Professor Peláez from Argentine that I already introduced at the beginning of the session. And well, I don't know why, but Professor Schmetterer is missing. He was supposed to be with us, and Mr. Shakirin was also supposed to be here. This is the that's sometimes problem with the online conferences, because you never know if anything can happen. There might be different reasons why people do not show up. So we have some other previous speakers like Professor Chen or Professor Said who will speak tomorrow. If you want to join our discussion, you are mostly welcome. Yeah, so David, what do you think? What we as doctors, what do we expect before AI can be implemented in practice? I cannot hear you. You are muted.
Sorry. Now it's okay?
Yeah, now it's okay.
Okay. Well, I think so. As we know, the artificial intelligence is one of the hot topics in our specialties, and we can see, or we can show today different aspects of applications in the clinical practice and the diagnosis and in the follow-up of the treatment, and in some particular subspecialties, for example, diabetic retinopathy of macular degeneration. Also, we can have important information about the follow-up of the patients and the best choice in the treatment. Of course, not in the all subspecialties we have the same information, but I think so in the next years we will see what happened in our subspecialties, and the way maybe can change, because not only in the professional aspect, also in the economics, and I think so it could be interesting, and we need to have the good information and the management of the artificial intelligence now, so we have better tools in the futures to these new technologies can make an adaptation to our present tools and the diagnosis and in the follow-up of our patients.
Yeah, thank you. I mean, I have a few comments regarding the presentation of Professor Schmetterer. As a matter of fact, I like it very much because he nicely presented many challenges for AI-based devices today. He shown one of the first slides, the eruption of publications recently. As I remember, we have about 1,000 articles per year on AI in ophthalmology. So it's a really high number, and probably nobody is able to read all of them. And probably there is no really sense to do that, because this is one of the challenges that we are quite aware that there's much more quantity than quality. So this is well, it's hard to say how which part is how much of this is really worthy reading. As a matter of fact, maybe we should have AI algorithm to help us to deal with that. Just to find the most important papers within this 1,000. And what I see from the field I am working on, this is diabetic retinopathy, that the great majority of papers, I mean, that are based on the algorithms that are registered, are coming from the owners or authors of this algorithm. So it is very difficult to find objective, independent studies providing, let's say, independent analysis. And these companies very often are not happy to allow other researchers to work on their algorithms, as a matter of fact. So how we as a final users, customers, rely on such an algorithm that were, well, majority, sometimes the only available analysis come from the people who might be commercially interested with the, let's say, results. This is one of the problems.
Yes, I am full agree with you. And for example, in combination with the Cleveland Clinic and the Professor Zhang, we published, I don't think so, more of 1 year, a paper about artificial intelligence in the diagnosis of small pigment lesions versus small uveal melanoma. And in less of 1 year, you have a lot of papers from the same topics from different companies. And as you say, is the companies with important commercial interest is made the analysis of the algorithms. Yes, I am full agree, but maybe in the future with probably more options and less commercial, or maybe with some rule of regulation of the good practice in this field, this could be changed. This is the reason, because this the international societies, with the collaboration of independent people of all around the world, maybe can make some recommendation regarding to this topic in the future.
Thank you. I see that Mr. Shakirin is with us. George, welcome. Gogi, welcome. And we wait for Leo Schmetterer. I received the message that he is going to join us soon, maybe. So, Gogi, would you like to share any comments about, have you had a chance to watch the presentation of Professor Schmetterer?
Yeah, I had a chance, and I apologize. I think I had some technical issues, so I was not able to connect to the discussion, but now it seems that it's solved. Yeah, so I think this is a very interesting topic. So I see it actually from two aspects, and maybe we can discuss it also a bit later today. What is actually, and for us as vendors, is very important to understand where we can help ophthalmologists or optometrists with AI. So because I'm hearing very different opinions there from, that AI should solve very complex things, and so to say, really be very intelligent, up to the opinion that AI should basically more take the routine work and maybe help some so to say, less professional or young ophthalmologists, just to, getting them more confident about what they decide. So this is one thought what I kind of want to bring into this discussion. And of course, we have all these aspects which were mentioned before during the presentation. Of course, we have, the issue of bias. We have an issue of explainability of AI and so on and so forth. But for us as vendor, it's very important to understand where, from your perspective as a user, so to say, we need to focus.
Well, I think that from my perspective, every AI application, as long as it is safe and reliable, would be welcome. I mean, and both of these directions. Finally, the problem we have as doctors with AI, it's both are related with the same subject. How much we can rely on this technology, so how much it is safe. What means how much it is reliable, and this is of course again related to the how much we can understand it. So the explainability. David, do you have any? Oh, Professor is speaking with someone. Okay, David, do you have any other comment on that?
Well, the same we discussed. I think so. Maybe we need to wait for more change quickly, but I think so now. Probably this problem with the objectivity and the independence of the elaboration of the algorithms could be one of the main problem in these papers. And also we have a really a lot number of papers published every month, every week, a lot of paper, but also some paper really, remember, this is it's a topic not only to the ophthalmology. You need expert in different fields. Probably some papers also we don't have all the information because we don't work in general in this field. Is a part of this field is news to us. Not only the application, we need to know the way and the programs and the algorithms to make this final diagnosis or in our patients. So I think so probably in the future we need again more regulation and more independent studies so we can really know what papers are good or works to us and what paper no. At the moment it's really difficult because the number of the papers is really a lot.
And another problem I see is that we have already mentioned that during one of the previous discussions in the previous sessions, is that there is a huge disproportion between the, let's say, open access and closed access models. So I would say that maybe about the 99% of all AI algorithms in ophthalmology are, let's say, not open access. So the authors do not allow anybody to test it, to verify it. Just a few examples of the other way. So this is certainly not supporting, let's say, reliable work on this algorithm, objective work.
Yes, I will agree.
Georgi, what do you think about that?
Yes, it's true. It's true. This problem now, especially in some countries, for example, in Latin America, we have strong limitations with the papers are not open access because really it's a high cost, some papers, and maybe in some countries you have some institution can open and offer these papers to the specialists, but
David,
not always.
I think algorithm open access, that the group, the authors, they let others to work on the algorithm and test it, verify it. This is my point. I mean,
I think, sorry, go ahead.
No, sorry.
Yeah, so I think that should be actually be a bit more requirement to the if you want to publish in a journal, that you also should at least explain in a very detailed way, where your data come from, how you implemented the algorithm. But the best case, of course, if you can also share your source code, that people can look at that and test by themselves, so to say. Because we, if we as an industry make a decision to productize one or another thing, we want to make sure that we ideally already have enough evidence that thing works. And usually a single publication is not, it's good, but it can be biased, so to say, and that's something which we think is not enough. So ideally it should be quite widespread solution and with quite some community support. So I'm also with you, Andrei. The more open approach we have, the better is for the the more independent evaluation we have of the one or another model, the more secure we are that the model really works in different conditions.
Yeah, and then I see another problem that, of course, we are quite aware that in many places of the world, AI applications are already sold, I mean, and entered, especially in this part of the world where there are no strict regulations. But even in Europe, as we know, we have about 15 registered AI-based devices in ophthalmology. As we know, in US, FDA is much more restrictive. So the danger is that because of possible harm that can be brought by any AI device somewhere, the image of AI for the future can be damaged. I mean, well, I don't want to say that forever, but reputation of this technology that was introduced, well, not well prepared, at least by some, can be seriously damaged. So this is my comment on that. We need to finish because we come, as you heard, my timer gave us information that our time is over. So just if you want, just we have time for one more comment on the challenges, or if you want to say something.
Yes, or maybe a short comment to what you said.
So thank you so much.
Okay.
Thank you.
The connection is broken. Okay.
Yes.
Please, Georgi. Yes.
Yeah. So maybe very short note from my side. Yeah, we need to find a balance between over-regulation and under-regulation. Yeah. So, and in principle, also for all medical devices which are in field and used commercially, there is of course a mechanism of complaints. This is must in EU and in US. So if the users see issues with that, so and there is always a kind of feedback mechanism, and that's also what FDA really now wants to implement. That we spend much more time looking of the performance of the algorithm, not only until we release it, but also when it works in production. And this is one thing. And another thing, I think we need to be very careful when we, when AI, what kind of tasks AI solves, that indeed we put some safety mechanism in order not to harm patient. And of course, I think the doctor still needs to be on the control seat and really make sure that the decision, he also understands the decision which is taken by AI, and only after that basically applies one or another thing to the patient.
Thank you, Georgi. David, last comment?
No, thank you. Very interesting, and congratulations to the meeting, Andres. And thank you, Georgi.
Thank you so much. So this is my pleasure to finalize our meeting. This is the last session, but I invite everybody for tomorrow. We have the second day of our AI in ophthalmology meeting. So we will be tomorrow with, I hope, majority of our audience and some of our speakers also. Thank you. Bye-bye.
Thank you. Bye-bye.
Thank you.
Thank you. Bye.